Welcome back to the course in the fundamental principles in Catholic bioethics in the program of bioethics here at St. Thomas University. Beginning always with a small prayer in the name of the Father, the Son, and the Holy Spirit. Blessed Trinity, we come before your presence, asking for your guidance, to be with us, to accompany us. We love you, we adore you, and we thank you on this feast of the archangels for the intercession of the angels and saints in our lives. We pray for your guidance in these issues of bioethics. We pray for peace on earth and reconciliation among all peoples according to your divine will. In the name of Christ our Lord. Amen. Father, Son, and Holy Spirit. Okay. Any comments or questions from previous lectures or anything? No? Okay. Little by little. How was that first assignment, the first homework? I tend to write a lot of stuff there, but basically I try to circle the key words, what I think is significant, right? And then put my comments on the side, what I think may have been missing or misunderstood. But I think you're all following along. You get the idea of the summary pretty well. And also typically I have a handout like I gave out today. And then I also post this, I will send you this. You can use this as a skeleton, if you will, to fill in for the lecture itself, all right? Just have to rearrange the furniture on the top parts. So I'll send it electronically as an attachment. And you can erase like everything that is above the line, for example, and then put, or all I need basically is your name over here, and the rest is ready. This is typically, I just put like a little review from the previous lecture there, okay? And then you have a pre-formatted structure skeleton that you can fill in, even if you want to do it electronically while I give the lecture. Some people do that on their computer, or do it at home later with the notes. See what I'm saying? But I'll send you this electronically together with the YouTube link this afternoon and the PowerPoint, the PDF of the PowerPoint. All right. Anybody having difficulty accessing the PowerPoint or the YouTube or anything, opening, you can open all that, all right? And also while I'm at it, we're supposed to be communicating with the STU address. I know it's kind of a hassle in the sense that it's one more address, email address to your list. Some of you may have 2, 3, I don't know. But there's a way of incorporating your STU address or emails to come to the other one, to your personal address if you want to do that. I don't know how to do it, but I know that some people do that if you want to, all right? But when we do communicate, I ask you to use the STU and also to look at the STU address regularly, because that's how the university communicates with you all right? Okay. Questions or anything there at any point, just ask me, whatever. All right, so basically we were looking at in the past couple of lectures, first the overall view of this bioethics, this Master of Science in bioethics, meaning that it's a multidisciplinary discipline. It's a inter-dialogue discipline with trying to look at the empirical world as it is, and also be honest and true to our beliefs and our faith, which will illumine the reality that surrounds us, actually gives meaning and makes sense to the reality that is around us. Those existential questions that Meyer asked, right? Where do we come from? Where are we going? If there is an afterlife or not? What is the meaning of what surrounds us? So that's why I like that textbook so much, even though it's out of print and people consider it nowadays passé, right? Yet, I think it's very relevant because precisely he starts with the meaningful existential questions in life. And then we go from there. Sadly, he lands on the opposite. Well, before I get into Meyer again, just very briefly, the whole idea of the program is to develop a theological anthropology, right? A theological anthropology, meaning a very rich and profound vision of the human person in context, in the sense that we don't live in a vacuum, but we are grounded in an Earth that is part of a planetary system, that is part of a galaxy, that is part of the universe. And so we also consider the environment, and even beyond the terrestrial environment, because of our technological capacity today, what some people are calling Astro Bioethics, because there is the possibility now of astrobiology. Think, for example, that there are organic molecules and fragments of macromolecules already in space, like DNA and proteins and so forth, flying around in space. You know, if that stuff lands in another planet, what's going to happen? Anybody's guess. But it kind of jumpstarts the beginning of life. Okay, because here we have to start from scratch, from inorganic compounds. So interesting, and because there's astrobioethics, then there can be also there's astrobiology. There can be astrobioethics. Like, did I talk about terraforming? Terraforming, right? The possibility of starting life in another planet. We have the technology already. So the challenges and the opportunities, right? A two-edged sword, for good or evil. What are the consequences? Can we even figure out the consequences, all of the consequences? Probably not. Anyway, so because of the advancement and the galloping advancement of technology today, my belief is that bioethics is a very relevant subject, very broad, because it tries to make sense and give meaning and direction to the technology that we're all engaged in. I mean, it's an extension of our beings at this point, right? Who would think of leaving a phone at home or a credit card? Got to go back home and get it. So it's challenging, and how to turn that into something positive, because one way or another, we have to kind of assume it's God's will. At least he's allowing it to happen in our time, right? And he probably, if it does happen, then he probably wants it. No, he definitely wants it for the good and not for the evil. Okay. All right. So that's kind of the big picture. Then this theological anthropology, a deep vision of the human person that is sacred, ontogenetically and phylogenetically, right? Just to recap, meaning the beginning of each individual human life on Earth, including our own, from conception to natural death, and the arguments that we can present to sustain that are credible. But also as a species, you know, as a group, we didn't just start yesterday or the day before by some kind of magical act of pulling hats out of a rabbit. Let's pull now a Homo sapiens out of this big hat. No, that would be magic. God does not work in magic. He works in mystery. So we're trying to really penetrate the mysteries of God by going back with what science can give us and see how far back we can get, how far back we can push the envelope of the Homo sapiens, and even just at the level of genus, can we go at the level of Homo, right, with a number of species. Okay, so that's kind of the big picture. And then this course in particular is, we're kind of bracketing the ontogenetically. We'll do that next semester when we look at the beginning of life and end of life issues. So this particular course is focusing more phylogenetically, the origin of humans as God's unique creation, and yet part organically of a world that is already existing around us. And therefore, we need to delve into evolution, okay? And evolution is a hot topic for religious people, but so is creation a hot topic for scientific people. To try to bridge that gap and do justice to both arguments, if you will, to both fields. All right. Okay, so the first half of the course is placing more emphasis on the organic or evolutionary aspect of it, to understand it, to bring everyone to the same page because we have various backgrounds professionally and academically. And kind of the second half will be more on the theological side of things. All right. Moving forward, so any questions? Again, Meyer spans the last century, which is the big growth in science. If you can think of the beginning of the 1900s, barely we had electricity, we had barely the steam engine, you know, it's the beginning of the Industrial Revolution. A century prior to that, but it really picked up exponentially last century with harnessing electricity, with circuitry and so forth, to what we have today, where we have jeeps roaming Mars, sending signals from there, digitalized and reconstructing that, where you can see actual images of Mars. And now the Japanese landed some robots on an asteroid or meteorite or something, some asteroid, right? And they're sending signals also over. The big thing now with these asteroids and comets and so forth is mining, extraterrestrial mining, because you've ever heard of rare earth metals, rare earth elements? There are these rare earth metals, which I should look them up actually, but they are components of contemporary technology because they have particular properties. Maybe they can withstand, they don't expand and contract, for example, with great ranges of temperature and things like that. China has pretty much the bulk of the rare earth metals on Earth, apparently, simply because they cover so much territory of the Earth. That's one part of it. But then that has economic implications and political implications and social implications and ethical implications all over the place. But what if some of these meteorites or asteroids may have some of these rare earth metals in abundance? Who's going to mine it? Who has a right to? Whoever gets there, is it just pretty much might makes right? You know, whoever gets there, that's kind of the capitalistic system. Huh? Whoever finds it first is theirs. There are some international laws that are applied also extraterrestrially, but there's no enforcement. Who's going to enforce that, right? So these are interesting, challenging things. Okay. So I just summarized it here with these two little lines. Heliocentrism and geocentrism, those two arguments kind of symbolize, morning father, welcome. They, to me, heliocentrism and geocentrism can go back about 500 years, 5 centuries, right? And it's the beginning of modern science. So modern science, we can say it's a very recent phenomenon. It only spans 500 years. Which in geologic time is nothing, okay? But truly, and if we consider Homo sapiens as such, maybe 200,000 years, 500 years is very tiny compared to that scale, okay? So, and it is precisely this argument, it crystallizes it. Heliocentrism versus geocentrism. It turns out that, well, you know, the argument, geocentrism, which had been held for millennia in many different religions, but especially in Christianity, it was a theological view. It's a pre-scientific view of the world and the universe and the planets and so forth, because of the incarnation, right, of the event of Jesus Christ, the God-man that occurs here on Earth, and therefore, theologically, the Earth had to be the center of the whole universe. But that theologically was implied because there were also religious societies. Consider art. For millennia, art is just religious art. Even when we go back to the cave people, which we'll see later in the semester, it's natural. And it was mixed with magic and superstition and all that, but all that points to the supernatural, points to belief beyond the grave. You don't see any other animal doing art. So art, one way or another, is some kind of a religious experience and a religious expression. Whether it's Christian or not is a different story. Whether it's monotheistic or not is a different story. But really, when you consider art, it's pretty much a religious expression of some sort, right? And so we are naturally religious. We're naturally spiritual. It's part of our nature. And it's an injustice to deny that. However, science, known today, when we say science, we're talking about empirical science. In other words, that which can be measured, right? And if it's not measured, cannot be measured, for science, it doesn't exist scientifically. But it doesn't mean it doesn't exist metaphysically or theologically and so forth, okay? All right. So then there's a shift to heliocentrism, and Copernicus and followers like Galileo, etc., were the ones who promoted heliocentrism based on empiricism, based on observation, which is the beginning of the scientific method, observation and experimentation. But it turns out that in the end, heliocentrism is also wrong, right? Because the sun may be the center of our planetary system, but it's not the center of the universe as such, because it's wedged, the sun, our planetary system is wedged in one of the arms of the Milky Way. We're not even at the center of the Milky Way. If we were, we would disappear because we will be crunched into a point of singularity, which is a black hole. It's pretty much, that's the standing theory today, that most, that the galaxies, the center of galaxies is a black hole. And that's why they have that spiral shape, but then there's a blank, and then there's it looks dark in the middle, like there's nothing there. That's because light is not exiting. That's how dense it is. So on. And therefore, geocentrism falls short, if you will, of, or it's not considering the physical reality around us. And yet, God did become man, so we have to consider the humanity of Jesus. And Jesus was subject to the natural laws of the universe, including gravity and so forth, and the strong and the weak force, everything else. That's what was holding his body together, literally. But heliocentrism itself is not correct, proper. It's estimated that the universe doesn't really have a center, even though it exploded from an origin. So it has an origin, but not necessarily a center. So the universe, different concepts apply when we talk about the universe as a whole, and what is the figure of the universe. It's very awkward for us. It's called a geodesic, which is an inverted, how a sphere, everything is convex, right? Everything is bulging out in a sphere. But it's the opposite. It's the mathematical opposite of a sphere. So everything is convex. It's bulging in, bowing in. And the best approximation, if we want to have a mental picture of the universe, is what is known as the saddle shape, the Einsteinian saddle. If you imagine a saddle bends like this and also bends like this, right? It's like if you were to take a sheet and drape it over a horse, like a saddle, it will bend this way and also bend that way. That's a geodesic. But even that is a very primitive and simplistic view of the universe, because then how thick is that, for example? There is no actual thickness. And what is outside of it? There isn't an outside and an inside as such, okay? So it really challenges our minds. We kind of run out of neurons, basically, literally. We can't go there because we don't have enough. The sophistication, our mind has not evolved to the point that we could actually comprehend that. Of course, we can comprehend other things. That leads us into this macroscopic, or I call it the super macroscopic universe, which is something bewildering by the immensity of it. In contrast to that, then this microscopic world that I'm calling, or universe, which is bewilderingly small, right? And the more we probe, the smaller stuff we find. How is that found, by the way, the smaller stuff? Well, you've heard of these super colliders, or hadron colliders, or the accelerators. For example, there's one in Switzerland. I had a privilege of going there a few years back on a conference precisely on a dialogue between science and religion, science and faith, which was started by CERN. It's called CERN, the Center for European Nuclear Research. In the United States, there are, I think, one or two of these colliders, and they're several miles in diameter. They go under the earth, and it's the tube accelerators. They accelerate protons, for example, subnuclear particles, to close to the speed of light, maybe half the speed of light, which is an astronomical amount, as you know. And then they accelerate in opposite directions, and at one point by magnets, all right, they make those two protons collide and smash against each other and see what comes out. If particles come out, if fragments come out, then those are, by definition, those are smaller than the protons, right? Those are components of the proton. It's like taking a car and smashing it. You eventually get a steering wheel, you get a tire, then you can take the tire and smash it apart again and get smaller and smaller. So that's what these colliders do. And they told us at CERN there that that event is photographed, the event of the collision. First of all, it takes several years to set that experiment up, and there are several thousand researchers connected online at that moment to get the data of the event. Okay, but the event itself is in fractions of nanoseconds or picoseconds, and they do, for example, 50 million photographs of the event in 1 second. Talk about bewildering. 50 million photographs in the 1 second, because the actual event is nanoseconds. Okay, it's amazing. Anyway, that was the beginning of the internet. Also, that's what the World Wide Web was founded there in the 80s. We'll get there. All this to say, there's a lot of fascination out there, but then if we don't control the technology will control us. So somehow or another, we have to, make sense out of it and direct technology for the good of humanity and not for its evil. Then the other thing that I pointed out, as brilliant as Meyer was in biology, he was simplistic with his theological analysis, because he just accepted the prevailing view of the time, which is a creationist, as a fundamentalist view of the story of creation. Specifically, they focus on, interesting that they focus on chapters 1 and 2 of Genesis, right? And even so, more 1, but 1 and 2, let's say, chapter 2, 1 and 2 of Genesis. Well, Genesis has 50 chapters. No mention of the other 48 chapters. Not only that, Genesis is only one of 46 books in the Old Testament and 27 books in the New Testament. So these creationists, fundamentalists, and the ones who critique that are focusing on this tiny little, they're looking at my pinky nail, and they're missing the whole body of the whole person, sadly. Okay, and that's what they call creationism. And so they're setting up a paper tiger that they shoot down, basically. But we don't believe in that paper tiger. We'll go much deeper into the mystery of the whole Word of God, and what is called the sensus plenior, to which we'll get in the second half of this semester. Okay. Oh, that was supposed to be a very brief review of what's been happening up until now. Better move forward. And so I'm gonna dim the lights, yes, so you can see better here. Try that. Definitely. Okay. Is that better? Or like the eye doctor says? Or is that better?
That's good.
Or is that better?
Yeah.
Okay. Better or better? Worse?
Worse.
Better?
Better.
Okay, then by default, we can also open this, the last one. You want to open that one a little bit, the last one at least? Because you get light from the back and you won't affect this too much. That's usually when we end up doing that. A little more for your notes. Okay, great. All right. Forward. So today we're going to look at evidence of evolution that we have in the world, and essentially from at least six areas where we have very solid evidence for evolution, the process of evolution, the fact of evolution, right? The evidence comes from the fossil record, from morphological similarities, from embryology, especially comparative embryology. And then this phenomenon of vestigial structures in the bodies of animals, and I guess plants too. Biogeography, you'll see what we mean by each one of these. Biogeography is another area. And the most solid one is really at the molecular level. That's the most comprehensive one and the most sophisticated one, needing, of course, more technology, but we have the technology today, like sequencing entire genomes, the DNA sequence of entire species of organisms. Okay, so these are different areas. They all converge, which are really not explainable by a simplistic view, a fundamentalistic view of creationism. Again, God just pulling rabbits out of a hat, but are very explainable in the process of the how, right, by evolution, by the process of evolution. So let's go right into it. Fossil record. Oops. I hope this is recording. Give me a minute. I think this stopped recording. Maybe just. Okay, yes. Sorry. I stopped sharing the screen for a moment, but we're back on. So let's look at the fossil record. I mean, this is stuff, this is material stuff that has been found on Earth, all over the Earth in different parts of the world, okay? Over decades now and centuries, these structures that look very much like animals and plants that are not around today. And this is not just rock formations. You can tell that these rock formations have a very particular shape, all right, that looks very much like skeletons. So it would be ridiculous to say, no, this is just a particular rock formation, or this is a work of art that some primitive individual did way back. No, I mean, these are real organisms that existed back then. You know, I mean, that again, the probability, I cannot tell you for sure 100% that this was an organism that lived back then, because I was never there, all right? But the chances that this was at one point a living organism is a 99.99999% chance. You see what I'm saying? Okay, so we go, because we're looking at stuff that is dead now, we cannot say 100% that they were living, but it would be ridiculous to say that these things were not living at one point. It would be absurd, right? Okay, so we have the evidence of these fossils. What do we do with them? Because they are certainly there in the shape, and we don't see these shapes today. And so that's what we call extinct. In other words, these are species that existed at some point, and they're extinct, right? Which they no longer exist as a species. And there are samples of thousands and thousands. At one point, I was collecting fossils, and then I was teaching at St. Brendan High at that point. And when I went into the seminary, I did one of these cleansings I do. Sometimes I do these periodical cleansings, and I basically just stay with almost the clothes on my back and give everything else away. So I gave away those fossils. I left them there in the biology lab at St. Brendan's. But I wish I had them today, because little by little, I was collecting different fossils from different parts of the world. And it was a small collection, but nice. At any rate, they're mostly the fossilized, they are the mineralized remains, hard tissue of animals, the bones typically. The bones are partially mineralized already, right, by calcium. And so nature continues to do that process and continues that mineralization process until they become actually rock. They do become, because rocks are minerals, okay? And so, but they are the rocks of organisms, of skeletons. Or it could be an exoskeleton, which is a carbohydrate, mostly chitin, but it's just a technicality. But it could be an exoskeleton, like think of a grasshopper or a cockroach that has an exoskeleton, no bones as such, but a hard shell. Or it could be an endoskeleton like all the vertebrates, right? Fish, mammals, birds, reptiles. And they get fossilized. Now, that could be the actual remains of the animal. You understand that a skeleton or a shell or carapace, mold is the remains of the animal, the organic remains of the animal, or it could be the actual animal embedded in amber. That is also a fossil, okay? If it's antique, because this could be a recent ant that got embedded in amber. But I'll tell you how we can determine that this is an ancient, that this is a fossil, is by dating the amber, by finding the age of the amber. And if the kid that creature is embedded in there, then it's logical to assume that it got embedded in there way back when the amber form crystallized. Okay. Just to point out that fossils are not just the remains, the organic remains of skeletons, but also animals that get trapped, mostly insects and plants also that get trapped in amber, for example, that becomes crystallized. Amber coming from resin of mostly of pine trees, of conifers, very little water content and it's thick. Also, plants are fossilized. For example, this is a fossilized trunk of palm. All right, it's now a piece of rock. It's mineralized, but it's a trunk of a palm. Or fronds of ancient species that are no longer around today. Okay. And also, a fossil could be an imprint, not the actual organic material residue, because that may no longer be there or available, but it can be an imprint. For example, the imprint of a leaf, that happens a lot in plants, because that's softer tissue, and over the millions of years, that tissue, actually the cellulose breaks down and there's nothing left of that tissue, so the tissue itself does not become mineralized. Sometimes it does, as in the case of this trunk, but other times it's an imprint, or also animal imprints, all right, including humans. And so the famous Lucy, until the bones were found, it was just a print of 2 feet walking bipedal locomotion, no 4 legs, all right, which was definitely a progress in the hominin line of the primates. So bottom line, it could be either the actual fossilized, mineralized organism, or it can be an imprint of that organism, whether it's plant or animal or bacteria, or it can be encased in amber or some other substance like that. But they are there. And so it means that they existed, and we can say that typically they existed millions of years ago. Millions of years ago. So that is a indirect, all this is inferred, right? Because evolution is a process that by definition has already occurred, because we're the latest product, if you will, of the evolution process. So we infer, but this points very strongly toward an evolutionary process. Then when we combine that, so how do we know that these things are indeed ancient? Well, because we date the rock in which they're embedded, or the strata. And that's why it's very important when one of these things is found, not to pick it up right away, but to do an analysis of the geologic strata where the fossil is found, so that it can be dated, put a timeline on it. And of course, in principle, the deeper we go, the older the strata, the stratum, right? One stratum, several strata. And in general, the deeper we go, the older the stratum. And therefore, the organisms or the fossils that are found in those layers will correspond to older fossils. And then one should see that more recent ancestors, more recent fossils, should not appear in older strata Otherwise, that would contradict this progression, this gradual progression of evolution. It should stand to reason that in the older strata, we shall find the more primitive or the older fossils, the older organisms. Okay? And that's shown here very evidently. For example, this recent stratum up here near the surface is showing a human skull that looks fairly modern. And also, but this guy looks like a skull of a mammoth here with a curved tusks. And in fact, Cro-Magnon and primitive humans coincided with the mammoth, especially in North America and Europe. We have evidence even from caves and the actual remains, not even fossilized mammoths, but some frozen mammoths with soft tissue, with intact tissue, whole mammoths that were frozen and have been discovered mostly in Siberia. And what some scientists have tried to do is to clone some of those cells to see if they can revive the mammoth. So far, they haven't been able to, because the closest eggs that they can use for the nuclear swap is an elephant egg, and the species is just too far away from it to match. Imagine if someone would ever succeed in having a living mammal in a zoo, a mammoth. Amazing, huh? Interesting. At any rate, those are recent animals, mammals, in the history of evolution, whereas older mammals would show more primitive structures and skulls that are not necessarily human, but they're anthropoid, meaning that they have the particular jaw, so forth, characteristic of the anthropoids, and also precursors or ancestors to the mammoth and to today's elephants and so forth. You see, and as we go deeper into the strata, we should be able to find older fossils generally. All right, so there's not going to be, if we want to find a hominid skeleton or skull down here in one of these primitive layers where the hominid line or the anthropoid line had not arisen yet, that would be a big problem for evolution to explain that. Okay, and so you look at, for example, they're concentrated mostly on the skulls here. You can see they are truly more primitive at some point, and these are all terrestrial skulls, but here this would be the skull of a primitive tetrapod that is called, in other words, a kind of an amphibian, the beginning of walking on land. But before this stratum in particular, there were no terrestrial skeletons found because it was all marine life and so forth. Okay, and even as we go further down into the strata, there will be no skeletons as such, no bones. It will be just invertebrates and more primitive crawling creatures at the bottom of the ocean and so forth. Okay, so there is a correlation between the antiquity of the fossil and the antiquity and the older stratum, geological stratum. You follow that argument, Emma? Mm-hmm. It depends. Some of these, a good question, because some of these deposits, first of all, there's some, the soil and the rock formation. There are different types of rock formation. There's sedimentary, there's igneous, and there is composite. And the best, in general, the best rock for fossils is, which one do you think? Like, for instance, igneous is from volcanic activity, like lava and magma and all that. Or let's say sedimentary, like a layering of mud or silt or sand over the eons. Which one do you think is more akin to mineralizing skeletons, to generating fossils? Igneous lava from volcanic activity or sedimentary rock? Well, what do you think happens to a skeleton when it's thrown into a volcano, for example? It's going to dissolve. It's going to be burnt up. It's going to be burnt, calcified, right? And not like it's going to be carbonated. It's going to be burnt, literally, because of the lava. There's not going to be anything left. Look at the lava advancement over there in Hawaii just a couple of months ago. It was eating up everything that is on its way, even cars. You think you're going to find a car after the lava goes through it? No. All right. So the car was literally melted and integrated into the lava. Much more for organic material. But how about sedimenting of a silt, like the delta of a river that keeps depositing silt over eons and eons on a skeleton of a fish that died and fell there? You know, that's actually ideal grounds for mineralizing and becoming a fossil, pretty intact, right? So sedimentary rock, what I'm trying to say is sedimentary rock is the ideal rock for fossils. And also shale, which you have for coal and natural gas, you have the three states. The liquid, which we know most commonly as petroleum or oil, right? Crude oil, the black duck is liquid. It's a thick liquid, but it's liquid. There's a solid version of that, which is known as coal or shale, even shale rock that has mineral particles in the coal, right? And then there's a gas version of that, which is what we call natural gas. All right, so shale is also very good. In other words, animals that got caught in the muck of petroleum. Imagine a pound of petroleum, right? Of black oil, and an elephant falls in there and dies, is going to be preserved by that petroleum, and eventually that petroleum is going to die. It's going to dry out. The vapors are going to come out. It's going to get mineralized, and it will become a rock that we call shale, or even coal is a little too black, too much carbon. But shale, which is a mixture, and shale also has a lot of fossils in it, right? And so there are different regions of the world where these sediments have been found, and they're rich, relatively speaking, they're rich in fossils, in contrast with other areas, like, for example, volcanoes, the skirts of volcanoes, which don't really have that much fossils, because whatever was there got destroyed. You follow me? So it depends. Bottom line, it depends. How deep? It also depends. How shallow that layer is, but in general, the deeper they go, the older the fossils will be. All right, and sometimes they go maybe half a kilometer, 1 kilometer. It depends what is exposed also, because we'll see now faceted mountains when there's uplifting and geologic events, even earthquakes and so forth. They may displace a whole layer of strata, which could be several thousands or millions of years old, and it gets exposed to the surface. Well, that's a tremendous richness. The geologists will go there and start searching for fossils all over the place. As it happens in Colorado and the Rocky Mountains, a lot of fossils. I got some. That's where I got some of the fossils. My brother and sister-in-law lived in Boulder, Colorado for several years, and we'd go visit and roam the mountains. So, you see? Okay. Yes.
When Mount Vesuvius happened, are they considered fossils?
That were mineralized, literally carbonized, not really fossils, because they're modern men. That happened a mere 2,000 years ago, so that's nothing compared to geologic time. Typically, geologic time is measured in hundreds of thousands of years or millions of years. That's pretty much the scale. So not really fossils, but if we leave them a few more hundreds of thousands of years the way they are, then they would be eventually considered fossils. Especially if the human species as such disappears, then they will be extinct, right? Another thing about fossils that the convention is that these organisms are now extinct. But the people in Pompeii, well, they were Homo sapiens, right? So we're not extinct yet. Yes.
The discovery of these fossils, it started after Darwin or before? When the people
for many centuries. it's not systematized. You have to think of it a little bit. Just put your person in the place. Mentally, you have to make this mental trip through history and consider ancient ones that were walking around and found a skull of a mammoth, to stay with the mammoth. What did they do with it? Well, some of them used them actually as art and painted over them and stuff, or carved them out. But there was really not much of an appreciation of the fossil as such. Some were destroyed, some were used for construction, who knows, or as a tool. It's only until recent, so really in the past 500 years, with the beginning of modern science, that there's a greater appreciation.
So we started to consider it as evidence of evolution in modern science.
Of course. Well, evolution as such with Darwin, right, in the late 1800s, the concept of evolution, and then this is going back looking at the evidence of evolution. But it's not that the fossil started to be a fossil in the 1800s.
No.
See, we have an appreciation for them as fossils in the 1800s. Okay. All right. And it kind of, you just made me think a little bit here. It follows a little bit the archaeology and the anthropology and the geology are kind of parallel sciences in this sense that there have been ancient civilizations for millennia, right? But the typical thing with ancient civilizations is that they would use the buildings and the materials of previous civilizations as construction material, and not necessarily we wouldn't think of taking apart one of the Egyptian pyramids, for example, to build an urban development today, or to build a port, with the big chunks of stone. And yet, in ancient times, the new king typically used the old king's city to build his own city, and they would dismantle. Even in the Colosseum was practically dismantled. Many ancient ruins of the Roman Empire were dismantled in the Middle Ages and in the Renaissance and in the Baroque to construct the palaces, and yes, even the churches and the basilicas with ancient materials. So there was obviously no consideration as such of value for antiquity. Or if they didn't use it for construction material, they would cover the city and build on top of it, which happened in Rome. So you have the medieval city and the ancient city underneath today's Rome, and that happens in many old cities in Europe, that there's an older city underneath, all buried. Or if they really wanted to make a statement of imperialism and sovereignty and authority, tyranny, they would raise the city, they would just demolish it down to the ground and plow over it and then throw salt on top of it as a sign and symbol that this older civilization will never rise again because we're stronger. And the Greeks and Spartans and those guys were typical for doing that. They did that in northern Africa, and a number of those older civilizations were destroyed sadly like that. They would burn libraries. The appreciation for antiquity is a fairly recent thing in humanity. And now we appreciate it so much that some of these things may end up in a private collection and it will cost several $1 million, something that is very ancient. And many times what you see in museums are copies because they're afraid that the original will get stolen. Yeah. Okay, so you see this is a work in progress, right? Even the human mind is a work in progress. Moving forward here, I wanted to show you that in theory, so this is theoretically, the older strata or the older fossils or the more primitive fossils ancestors will be in older strata, right? And that's the theory. But even here already is showing a little break, a fault that will displace some of these layers. And also here is showing a layer that is not totally contiguous because there's a little bit of uplifting here. So what I wanted to say that in reality, this is what's happening. So the crust of the Earth is really a dynamic system. It's a dynamic system. It's just that that dynamism is very slow, right? It's like the turtle. The turtle is slow, but the Earth is patient. So in the patience of the Earth, all this is going on over the billions of years. And we're talking about, I'll show you a little bit more detail, continental drift and plate tectonics, how the continents are basically like rafts. If you can think of it, a raft or a floater on top of on the pool or the ocean. And these rafts or floaters, when they come against each other, they beat against each other or they rub and scrape. And that's what causes mountains. That's what causes earthquakes, the Pacific Ring of Fire and things like that. So there's all this dynamic activity happening right now on top of the Earth, on the crust that we're standing on, but it's very, very slow, extremely slow, again, measured in terms of millions of years. And yet relatively fast in geologic time. For example, Europe and North America are separating from each other, the continents, at a rate of maybe 4 or 5 inches a year, which is really very significant. That can be definitely measured by satellite and laser beams, okay, with great precision today. So it is significant for geologic purposes and for the purpose of fossils. What does this mean? Well, it means that it's not going to be as clean as this, right? This would be ideal, and it does happen in some places, some localities, but in other localities, what do you have? So here's one that is fairly horizontal. Here's an older layer down here. Obviously, you can see that this is mostly shale or carboniferous, right? And this one is more sedimentary, just from the color of it. But you can see definite strata there, very, very pronounced strata. All these can be dated, and I'll tell you in a minute how we can put a date number, all right? How many thousands of years or millions of years ago did these sediments form? This one is fairly horizontal. You can see it's along the road somewhere, but not always. Look at this jagged formation, and the jaggedness is vertical, all right? So this had a double, look at the layering here, right? So that is pointing to what, think of natural phenomenon. How did that happen? Well, it happened like this, sedimentation. But it's now moving vertically. So this used to be horizontal is what I'm trying to say. This used to be, can I do this? Yeah. Right? Those layers of sediment formed that way, horizontally, because it's deposition, right? The riverbed or something, and or a delta. But then it got also wrinkled. So it became vertical and wrinkled over time. So obviously, you know, you have to be very creative. And when you're going to date this, I would say you start here. Hopefully this is the younger layer and this is the older layer. And you would go this way, but you're actually going horizontal. You're not going vertical on the horizon. Or you're going older in time. You understand what I'm saying? Again, maybe more confusing, but you see the jaggedness of this, and this is real. Many layers are like that. This is kind of the exception, to find them so neatly organized, one on top of the other, horizontally, okay? Also, here's another wrinkling, but this wrinkling is horizontal wrinkling, and you can see there's a buckling up here, and then there's a dip and so forth. That actually forms mountain ranges. Then you also have, even if you have horizontal layering here, which is very evident, the horizontal layering, there's erosion. In other words, this used to be a river that was up here, and over the eons, that river ate right through the sediment here and deposited all that sediment out here on the shore, on the delta, and there should be this river down here that over eons has carved through, like, for example, the Grand Canyon. Grand Canyon used to be flat at the top in the Midwest, right? And it was carved out by the river going through it over millions of years and taking that sediment out and down. So imagine all the sediment that used to be here is now out here. There may have been fossils over here originally that landed over here at the delta of the river when it was pushed out by the floodwaters. Depending on what the season was, it was very rainy season, or if it was a dry season, and so on and so forth. So bottom line, is a very dynamic system that takes a lot of expertise and patience to try to figure out which are the oldest strata, and therefore the more primitive fossils and so forth. Okay, you get the picture. Now, we've been talking about dating putting a timeline on these strata. How do we do that? Maybe I can do this a bit bigger. I can refer to the previous slides on this side a little bit. Yeah, I still have margin more. That's about it. Okay, so this is how we did it. Basically, we use a technique called the half-life. All right, you've heard of it for carbon, for example, carbon dating. Well, carbon dating is one of them. Here's it turns out that those are the elements of the table, right? The periodic table of elements, or the periodic chart in chemistry. Each element has a unique number of protons and a unique number of neutrons in the nucleus, and then a unique number of electrons orbiting around. That makes the atom stable, and that is what we call the atomic theory, the standard model, which is still prevalent as the basic unit of matter. If we go subatomic, by themselves, they're not stable. Just a proton by itself or an electron by itself is not stable because it has a charge, it wants to do something. So they coalesce in atoms that stabilize them, right? All right, so each element on the periodic table, beginning with hydrogen, with one proton, all right? And say to carbon, the normal number for carbon is carbon 12. That's the number of protons, and therefore electrons and so forth. But it can have a varying number of neutrons. That's what makes what is called the isotopes. All right. So when you see carbon 14, it means that it has two more neutrons, which can decay precisely by the weak force. Right. The decay from carbon 14 to carbon 13, with one of those neutrons decays, and then when a second neutron decays down to carbon 12, which is stable. And that carbon 12 will last millions of years because it's stable. But the 13 and the 14 are unstable because of those excess neutrons, all right? And so that decay process happens over a period of time. And it's like a fingerprint, but it's a chronological fingerprint. It's a time fingerprint or an age. The better analogy would be like every species on Earth has a particular timeline, a particular age, the average age. What's the average age for humans? We have to go country by country because of healthcare availability and lifestyles and so forth, but generally it's around 80 years of age, right? Women 82, men 78, so you get to endure 4 more years than we do. This valley of tears, you probably did something wrong to deserve that. Just kidding. You gave Adam the apple. No, but you see what I'm saying? Every species has a particular timeline, but then there's variation, right? Each individual, and it's not that we all die at 80 or women die at 72, 78, and you die at 82. No, there's an average, okay? And that's the norm. So that half-life, the half-life is pretty much the time that it takes for half of the material to lose, if you will, its radioactivity, okay, to become stable, all right? So for example, and that graph is a logarithmic graph because you're taking half each time. The radioactivity is diminishing by half. In other words, if I had 1 kilo of carbon 14, right? By the time I have half a kilo of carbon 14, right? The other half kilo is going to be carbon 12, all right? So that decay takes a particular amount of time for each element. So it's like a signature. Just like each species, we last an average of 80 years. Other species last longer, other species last shorter, on average for that particular species. The same with the elements, okay? That's what's called the half-life. And it's a logarithmic scale. It's not linear, precisely because one is taking the half time. I can give you another little analogy. You ever done that mental trick of trying to get to the wall? If I start from here and I travel half the distance every time, will I ever get to the wall? hypothetically or theoretically, I will never get to the wall itself. Because imagine, okay, so I'm here, I will go half the distance first, okay? Okay, so that's half the distance, more or less. Then I will go half this new distance, all right? So half the new distance. Now half the next distance, half the new distance is this, half that distance is this, half that distance is this, and this, and this. But you see what's happening is 1 over x, and x is doubling, right? The fragment, so it's 1 over x. You're increasing the denominator, really, and how much can you increase the denominator? To the infinite, because if you give me a number, I can always give you a number that is half of that number, right? And half of that again, and half of that, so it's 1 over infinity. So theoretically, mathematically, if we travel half the distance toward a fixed point, we will never get to the actual fixed point. It becomes asymptotic, it becomes exponential. All right, well, never theoretically. In practice, you know, the shoe cannot measure that smaller distance. When you get down to the millimeter and the fraction of a millimeter and a nanometer, my shoe's not going to pick that up. You know, at some point I'm going to touch the wall. So it's a question of precision, right? However, the half-life comes out to be a logarithmic scale, and that can be measured, right? So if you will, the first half-life is what's significant here, the first half-life, and that has a number. So for example, for carbon, or carbon-14, the half-life is 5,730 years. Okay, so if I find organic, bless you, and this carbon-14 data is particularly significant for fossils because fossils have carbon in it, right? Organic material. So organic material, by definition, has to have carbon and hydrogen, bless you. But the one that's important is a carbon. A fraction of that carbon is going to be carbon-14. Most of it will be carbon-12, but some of it will be carbon-14. And whatever is left of that carbon-14, we can figure that it was twice that amount 5,700 years ago. So we can date fossils fairly accurately by using the half-life dating, or sometimes it's just known as carbon-14 dating. All right? It turns out that, as I mentioned, every element has a half-life. Some of them are in the area of seconds or fractions of seconds, typically the smaller elements, but not necessarily in general. And then they start increasing in time. So for example, lithium, right, which is number 8 on the periodic table, has, well, this is the isotope actually. Where's the system over there? Yeah, number 3. Give me a minute. Is the half-life of lithium, radioactive lithium, is a fraction of a second, 0.8 seconds, and not even 1 second, all right? So it decays very fast, in other words. It decays, radioactive lithium decays very fast. Whereas krypton, for example, takes 3 minutes to decay, 3.16 minutes. Right? Oh yeah, here's the chemical number. Sodium takes 15 hours. Radioactive sodium. Iodine is another one that is used in the lab quite frequently for tagging. 8 days, so 1 week, more or less, a little over a week. Then we jump to years, thousands of years, and millions of years with uranium. That's why uranium is also very good for timing geologic time, especially the older strata, because the half-life is in the millions of years. But it's a very accurate number, as you can see, 503 million years, 700. You don't have to remember the actual years, but the ones that is most used is carbon for organic material, and then the large elements for geologic time itself. Who had a question? Andrea?
Although we use only carbon for fossils because of the organic materials, right?
Well, yes.
The other ones too.
Because the other ones, for example, what else would you find? Calcium in a bone, for sure, calcium, but calcium is very, has a very small half-life. Yeah. So, and by the time that the fossil is mineralized, you know, there will be other minerals that have replaced that calcium. And so, but carbon is more stable, and so it lasts longer, and it's very good. But when we go, the other thing is, it could be older than 7,000 years, because some fossils are in the millions of years, right? So we have to use other, we have to go indirectly by the strata where the fossil was found, by the stratum. Right? And the stratum, yes, we can use other elements. Okay, all this to say that we can actually put a timing on these layers, the date, and then the fossil that is embedded in that layer generally stands to reason that is that old. But keeping in mind that these are also dynamic strata that can move around and shift, and sometimes they can reverse, and an older stratum can be on top of a newer stratum, okay? Geologists know about that. The end result then is, as we start putting these fossils in a map, if you will, or a diagram, is that we come up with these branching diagrams where we can put older specimens, older fossils back in the diagram, and then younger fossils forward, and we can create, in fact, a branching diagram that is also known as a cladogram. Cladogram coming clad or group, a clad or a clade, depending if you are the British pronunciation or the American pronunciation. Some people say tomato, some people say tomato. Cladogram or cladogram, most people say cladogram. It comes from clades or clades, which is a group, okay? Group of organisms, typically like a phylum or something like that. Or, okay, so you see here, for example, this diagram will tell you graphically that the shark is older than, or diverged, not older, but the shark is living today, so it's not older, but diverged before the frog. And the frog diverged from the common ancestor, right? The ancestral line, this is the ancestral line. The frog diverged before the rabbit. The rabbit diverged before the sparrow or birds. These are representative groups. Okay. Now, what's interesting about this branching is that you see these points, these junctions here. The junction is what we call the nearest common ancestor. The nearest common ancestor is at the juncture. In other words, at this juncture between the reptiles, represented by a crocodile, and the birds, represented by the sparrow, here, this juncture is a common ancestor. Now, what's the intuition? This common ancestor should have characteristics of both, should have characteristics, reptilian characteristics, and should have avian characteristics. Finally, at the juncture here, on the branching point, that's what is called a nodule or node. It's called a node. And this node here, this fossil should have characteristics of both. And in fact, a few of those fossils have been found. One that is very well known is the Archaeopteryx. Archeo just meaning primitive. And pteryx is a reference to the wings, primitive winged creature. Here is the actual fossil, all right? You see it's embedded. What's your intuition about this rock? You think this is igneous rock or sedimentary rock or calcareous rock? What kind of rock do you think this is? From the color and kind of the texture of it. Sedimentary, right? This would be like silt or mud that got compressed and this fellow died and got embedded in there. Excuse me, not only can you see the skeleton, but you can actually see the feathers, what made up the wings. All right, look at that, amazing. But you can tell that it definitely has a tail, but it's a wing tail, see here, okay, and has hind legs, but the forelegs also have claws, which you see any birds with clawed wings? Bats have clawed wings, but bats are not birds, bats are mammals, okay? So you see it has characteristics of birds, but it also has characteristics of reptiles, where all four wings are clawed. The four legs of the reptiles are clawed, right? So this is a reconstruction. This is not a living fossil. This is a reconstruction, a model of an Archaeopteryx. It's anybody's guess what the colors were actually like, or the patterns. But they tried to match more or less. How would they do that? They would try to match whoever was this our biological artist, right, or archaeological artist. They would try to match more or less the sedimentation. So they have to put a whole picture together, they have to put a whole ecosystem together. If they found some, let's say they got lucky and they found some fossil plants embedded in the same layer, maybe a little further away, they could try to reconstruct a little bit the forest or the little bit the environment in which this creature lived. And then they can try to figure out more or less what the color pattern would be. But it's speculative. The color pattern is going to be speculative on the fossils, okay, on the reconstruction. What is not speculative is the actual structure of the fossil itself. This is a skeleton, bar none, and these are feather-like structures, bar none, okay? And other characteristics. Have you ever seen a bird with teeth? Living birds, no teeth. It's just a beak, and it's made out of collagen protein, all right? Not calcified like teeth. But this is a skeleton, this is a skull of an Archaeopteryx, and the teeth are very prominent, which are reptilian teeth. In fact, the whole skull like that, one would be hard pressed, just the skull, to place it as a bird or a reptile. It's looking more similar to a reptile with homodonts, with cone-like shaped teeth that are homogeneous, not heterodonts like the mammals, have different types of teeth, different shapes. So the homodont cone-like teeth are more typical of reptiles, right? Okay. But winged. So Archaeopteryx most likely would be at the node between the reptiles and the birds. Interesting. Also, and this guy has been dated to about 150 million years ago from the sedimentary layers, right? Not the organic material, because we cannot go that far. But the sedimentary layer, found some uranium there, or whatever, and was dated back then. Another example is, so seldom do we have a fairly linear progression. Typically, it's a branching, okay? But every now and then, fossils are found that make a fairly good case for a rather linear progression of ancestors. It's rare, but the case has been made for the evolution of the horse, or the horse genus, which also includes the donkey and the giraffe. All right, no, sorry, the donkey and the zebra. And there's another, what is it called? Onyx or something like that. Well, there's another animal in Africa that is horse-like, is from the Equus genus. Here we see the skull beginning with what used to be called Eohippus. Eohippus, a primitive horse-like creature that back then was the size of a dog, more or less, kind of a large dog, okay, or medium-sized large dog. That was the original horse, if you will, or horse ancestor. Sorry, not truly horse, but horse ancestor. Today it's called the Hyracotherium. used to be called Eohippus, or original horse-like creature. You see the 4 of the 5 toes, 4 of the 5 digits, right? The first digit would be up here somewhere, the thumb, 4 of the 5. And look at the evolution, okay? The next, this is about 55 million years ago, 55 million years ago. And then about 40 or 45 million years ago, about 10 million years later, some other fossils were found that showed a development of the hoof favoring the middle finger, the third finger, or the third toe, third digit, all right? Favoring that one. And the other 2 or 3 of them becoming degenerate. This is what we will call vestigial structures. They're no longer, so this animal is landing more and more on a single digit, the middle finger, the middle toe, right? And the other 4, meaning 1 and 2, 1 is already degenerate way up there before it got to the Heliocentrism, but the other 4 digits were still functional down here. Okay. Now digits 2, 4, and 5 are becoming degenerate. That middle finger continues to be favored by evolution, so that another 10 million years later, other fossils were found where the other digits are becoming more and more degenerate, okay? Until we get to the Equus genus, Equus, maybe 10 to 15 million years ago, with the single digit predominant, and the others not even barely a remnant. And of the digit, the hoof, the nail, which is what makes the hoof, is actually the nail. So that's cartilage. That's not even bone or cartilage. That's protein. That's keratin protein, just like our nail, but super big and super hardened, right? And so the horse and the donkey and the mule and the zebra, they all walk on their nails, on 4 nails. Each leg, the whole weight of the horse. So imagine the very specialized evolution that has happened on that finger, on that digit. And to match the overall size, instead of getting smaller, has gotten bigger. Because that's probably, I don't know what's pressuring what here, but they're concomitant growth and development, if you will, the overall bulk, mass that digit has to carry. And so it becomes stronger and stronger. Imagine, just compare this anatomy to this anatomy down here, all right? And also the skull has gradually become larger and larger, okay? More and more grazing type of, where the front teeth are clippers essentially, but then a lot of molars for grinding, chewing the cud, right? Okay, so that's another example. Seldom is there such a clean progression over the millions of years with enough fossil record to back it up, both at the level of skeleton, overall size, and therefore the bulk size. So you can see from the original ancestor of the horse to the contemporary horse, all the development that has occurred. So this gives us phyletic lines, that Eohippus would have been over here, right? But these are now contemporaries. These are all contemporary Equus, which is the genus name. Here it's giving you the actual species, right? This is the Cavallus. This is the actual horse. I think this is the zebra here. And then there is the ass. And these are these other horse-like creatures that live either in Africa or in the Middle East there. Okay? But these are different species. Now, these are all contemporaries. So these are not ancestors of each other, but they do have common ancestors. And so I can ask you, excluding this one, I don't know why they didn't start here with a numbering, but excluding this node, how many nodes are there? Excluding the original node. How many nodes? There's a specific number. 8 nodes. 8. 1, 2, 3, 4, 5, 6, 7, 8 nodes, right? Each node represents a what? The nearest common ancestor. For example, what is the nearest common ancestor between Equus onager and Equus quiang? What is the nearest common ancestor? Whatever is number 3. Okay, whether it has been found or not. That would be the nearest common ancestor to these two species. What is the nearest common ancestor between onager and somaliensis? What is the nearest common ancestor between onager and somaliensis? Number 2, not 4. 4 is the nearest common ancestor between somaliensis and asinus, right? 2 types of donkeys. So you see how it works? The nearest common ancestor between onager and cabalus, and the horse, what's the nearest common ancestor between these 2 guys? Not even 1, because cabalus is not a 1. It will be here, -1 or 0. This one, this common equus, which maybe I'm just guessing that the numbers represent as skeletons that have been found. Maybe this one has not been found. Okay. But just by looking at these figures, at these shapes today, these are all contemporary animals, right? It is undeniable when we see the shape of onager and when we see the shape of a horse, it's undeniable that they're somehow related, right? I mean, they don't look like frogs and palm trees. And so they have to have a common ancestor somewhere. Maybe it just hasn't been found. Okay. All right. So you notice how I've shifted before up until here. I was talking about the fossil record, all right? Now moving forward to contemporary species that are related. Contemporary species that are related. When we look at different types of monkeys, well, they look more like each other than they resemble each other more than flies, for example. Okay, and different types of flies resemble each other more than mango trees, and so on and so forth. You follow me? And so we can start putting together, just from the 2 million species that have been classified today, we can start grouping them into similarities. The most obvious ones are going to be what? Morphological similarities, anatomical similarities. Does it have 4 legs, or does it have fins? You know, does it have fins, or does it have leaves? So we can start grouping them from the most obvious anatomical morphological shapes into groups. But then we're going to find that within these groups, there are various species, because a horse may look similar to a zebra, but it's not identical. And so we can get more and more specific, and we can generate these different species categories, if you will, for now. What I'm getting at is taxonomy, or the classification of species, of the contemporary species that we see, not fossils, which is very sparse. That's what paucity means, okay? Here I'm talking about contemporary species, of which we have discovered and labeled, named with scientific name, about 2 million, more or less. 2 million species between animals, plants, and fungi, and the bacteria, which are not really typical, they're not named as species, but they have an analogous scientific name. types, right? But these are contemporary. These 2 million species that we have labeled, classified with a scientific name are contemporary. They're living today. It implies that because many of these can be grouped into similar shapes, right? It implies that they have a common ancestor. So it infers evolution because a common ancestor is no longer living, but it must have been a common ancestor. I'll give you the even more solid proof, and we'll look at the molecular evidence, and you'll see what I mean by that, particularly DNA as the universal molecule of inheritance. Just getting a little bit ahead of myself here. But I want to move into then the classification of species, which is this whole field of taxonomy. Remember Linnaeus, Carolus Linnaeus, right? The Swedish fellow from the 18th century, 1700, who started naming species by first name and last name, basically what we call the scientific name of species. To this day, it still stands. We call it a binomial classification because the reference is to 2, right? Just like we also have 2 names, Alfred Chaffee. I have my personal name and I have my family name together. So similar, Homo sapiens. The Homo is the genus, okay? And the species is not sapiens. The species is Homo sapiens. In other words, the species includes the genus. Sometimes abbreviated H. sapiens or E. caballus, right? But the species includes the genus. So the species is binomial, because that anchors it at least 1 layer up to some other hominins that may not have been sapiens, or to some other equus that may not be caballus. Hello? Okay, so that's the scientific classification. We thank Linnaeus for inventing that, and so it's called the Linnaean classification to this day. His name has remained embedded in there. And it is a scientific classification of species. It is also Latin, and there is a hierarchy established. The hierarchy is done by groupings of similarities. Now, the similarities are most likely anatomical or morphological, shape, but they can also be physiological by metabolism, and then it can also be behavioral, and ultimately they're going to be molecular, all right, the similarity. And that's the most comprehensive similarity is going to be molecular, and that's when we start looking at molecular homologies to establish the hierarchy, the hierarchy of classification and the groupings of all living organisms, all right? Don't worry, we're getting there step by step. For now, we're still on the morphology, on the shape of the creatures, how we can group them. Obviously, different types of bears, different species of bears look alike, and they look more alike to each other than they look alike to turtles. And different types of turtles look more alike to each other than they look alike to whales, and so on and so forth. Okay, so the different groups, you see how it goes? So we begin just pretty much by the external morphology, and if there's a question, because 2 different species may be looking very similar, we have to go deeper, and the ultimate criterion is going to be really at the molecular level, at the genetic level, at the DNA or the genome, all right, which will be unique for each species. We're getting there. So let's follow this classification, beginning with the species. And in this particular diagram, the species is the American black bear, which happens to look black. Sometimes the American black bear looks brown, and sometimes the American brown bear looks black. So there's a little bit of confusion there. But This one shown here, this American black bear actually looks black, all right? So that's Ursus americanus. What is the genus? Ursus, right? What is the species? Ursus americanus. Or if you want, U americanus or U americanus. All right? Okay, so we have one species. Then we're going to walk around North America, because this is Americanus, and it turns out we found other bears that are not black. They're brown, and they are more bulky and kind of husky and not as slender as the black bear. So we're going to call that the grizzly bear. Okay? It's a different species, but the same genus because it's an Ursus. Anatomically, generally, it's about the same, and it has the same typical behavior, the same general behavior, which is that bears normally are hunters, right? Or carnivores or hunters. Then we go further north, and it turns out we found that they're also all white. So how can a black bear be white? Not albino, all right? And therefore, there's another type of bear that we found, that's the polar bear. So here is represented by three species by the same genus, Ursus, by three different species. Okay. Well, this was North America, but how about we go to another biome? How about we go to South America, or we go to Europe and we find other types of bears, and if we move further geographically to Asia, we find other types of bears, all right? But they are more distinct than the North American bears. And so we bump it up to a broader group called the family. Okay, and the family is the family of Ursidae, which means that under the Ursidae, there's going to be genus Ursus, but there are going to be other genera that are not Ursus. Okay. So we're at the level of family. So one family will be made up of two or more genera. One genus, several genera. Follow? This is the extra Latin that you're getting in the course. So for each genus, one or more species, two or more species. Some genera only have one species, as for example, Homo. The only living species of Homo that we know of today is Homo sapiens, living. So far, we haven't discovered any non-human, non-sapiens Homo living today, all right? Other genera have many species. Families would have more species, right? Because it covers several genera and so forth. We go up further to a larger group, more inclusive, in other words, more diverse in morphology, in anatomy and physiology, but generally the same kind of general behavior. We end up with an order. So one order will have several families, and that order is precisely based on behavior. Carnivores or meat eaters, because they're carnivores, they tend to be hunters, and they also have particular shape of teeth. The teeth are made more for tearing and slashing, like the canines, precisely. The canine teeth come from the carnivores, right? And even the molars are more for cutting than they are for grinding, because they're carnivores, they're not herbivores. They don't have to chew the cud, they don't have to grind, they have to cut and tear through tissue of the prey. So that's at the level of order, you see? Further up is the class. So class is even more inclusive. It's going to include carnivores and non-carnivores. So the level of class is going to be mammals, sticking with the original bear, all right? There are other classes that are not mammals. For example, birds or reptiles. Those are all classes, right? But because we're started with the bear, then this class of the bear is going to be mammals. But mammals include other orders that are not bears. It includes, for instance, the wolf, It will include cetaceans, which are the dolphins and whales. It would include ungulates, the ones that walk on their unya, and they walk on their nails, right? Mm-hmm. So a class will include several orders. Higher still is the phylum, and this is another large category, phylum. Okay. And there are about 3 dozen phyla in the world today, approximately, depending again how they classify. This is a dynamic system, and there are some groupings that have been very established and others that are still under questioning. So the scientific classification may look very static and rigid, but it's not, it's a dynamic system, okay? And there are classification keys that are very elaborate and detailed. But there are approximately 3 dozen phyla in the world. And here, all of the plants and animals and fungi will be classified in these phyla. But then it gets very small quickly because we only have 2 more layers of hierarchy going up from, excuse me, from the phyla. And you notice that the phylum for the bear and all these other creatures that have been expanding into the grouping is Chordata. We're more familiar with this like vertebrata, the vertebrates. But the vertebrates is actually a subphylum, or because the chordate is the phylum. Then above the phyla are the kingdoms, of which there are only 6 or 5, again, depending on how you classify them, but 6 or 5. And here we're used to hearing about the animal kingdom, we're used to hearing about the plant kingdom. Maybe you've heard about the fungi kingdom, mushrooms and others. But then there's also the bacteria kingdom and the archaea kingdom, which is more primitive than bacteria, but very similar, all right? And so we go higher than kingdoms. Kingdoms can be classified into 3 domains, and this is the broadest category, if you will, the most inclusive category of all living things. So these 3 domains: the eukarya, the bacteria, and the archaea. I'll show you a diagram of that. I gave you a diagram of that at the beginning of the semester. So, but domain is the largest one, and today the current standard is 3 domains. So 3 domains, which are made up of 6 kingdoms, which are made up of about 3 dozen, 30, about 30 phyla more or less, and then hundreds of classes, thousands of orders, thousands of families, and so on. So we get to 2 million different species, right? Different species. This doesn't say anything about the individuals in that species. It could be a single individual, which is very, very close to extinct, you know, it will be extinct tomorrow. Or it could be super abundant, like bacteria of single type. But this is just the hierarchy itself, all right? Scientific classification. Forward. Questions? No? Got it? All right. Sticking with the morphology or the shape of the structures, again, this is another line of evidence for evolution. Remember, of the 6 that I had listed originally, right? Talked about the fossil record. Here we are in morphological similarity. We're going to look at some structures that are homologous structures. They have a common origin, but currently they have a different function, all right? Homologous structures. Let's go there. Here we go. You've seen these diagrams many times. These are the 4 limbs, 4 meaning F-O-R-E. These are all vertebrates of different. The forward limbs. in contrast to the hind limbs, right? All right, so let's look at a human arm, for example. You got the humerus, radius, ulna, or cubitus. We used to say cubitus. We don't say cubitus anymore. Anyway, these are what makes the arm, but the hand itself, we got the carpals, the metacarpals, and then the phalanges, which make up the fingers. Whereas in the cat, and we use the hand for what? We use the arm and the hand for grasping, not normally for walking once we are beyond 1 or 2 years of age, right? So we use it for grasping. That's the function. But then we look at the forelimb, the forward leg of a cat, and we find that it has a humerus, radius, ulna, has all the different structures, okay, but somewhat different shape, more adapted to its function, because now this forward leg or this forelimb is used for walking, not grasping. It will grasp occasionally when it's catching a prey, but normally used for walking, different function. Okay. They're more drastic in the cetaceans, in the marine mammals, which are whales and what else? Dolphins, orcas, and also this guy over here, the protected, that is freshwater manatee. Thank you. They're also marine mammals, right? The nose migrated to the head, but they have lungs, not gills. Well, it turns out that the forward limb, the flippers on the front, also have adapted same structures, the same skeletal bones as all mammals, which is the humerus, radius, ulna, they can be traced, the carpals, and then the digits are super elongated and extra phalanges, and all covered by a flipper for swimming, navigating, not walking, but the equivalent, not grasping, but for swimming, all right? Different function, but the same origin. It's undeniable that these bones have the same origin, right? The bat, which is another drastic one, a flying mammal, technically the only truly flying mammal, a different species of bats, different genus of bats. They have also the arm bones, but again, the digits are extended for particular function. And then there's a membrane of skin in between for flying, which is very different than swimming, than walking, than grasping. Okay, so you can see that there are different functions. Today, these are what we call derived characteristics. But all these points, we can infer a common origin. In other words, all these four creatures somehow must have derived from a common ancestor that had these bony structures in them. And then they evolved from there forward to the derived structures that we see today, the specialized structures. So what we could conclude from this is that most likely all of these four different creatures that inhabit different parts of the world, and whether it's on land or on the water, have a common tetrapod. Tetrapod, a four-legged creature from where these structures developed. And this is just the development of the forward limbs in contrast to the hind limbs. We'll also talk about the hind limbs in a moment, and especially the socket for the hind limb, which is the sacrum. Okay, so you see how all of those structures, which we find them all over the place, are pointing toward, infer a common ancestor. That all these contemporary animals must have had, and plants too, must have had a common ancestor at some point. Another line of evidence. Let's see. I think this is the third one, right? So after we do this, we'll take a little break.
I think it's the third one, comparative embryology. Yeah.
You follow so far? So we've talked about two different lines of evidence, the morphological structures of contemporary animals, and also the actual fossil record that is on the now is there in front of me that can be dated back to millions of years ago. Now, let's look at comparative embryology. So we have different species, all right? All these happen to be, again, vertebrates, fish, amphibian, reptiles, birds, mammals. And these are designs, these are simplified graphics, caricatures of embryonic development in different stages. We can see that earlier stages are more similar to each other among the different species, even different groups like mammals, birds, reptiles, fish, amphibians. Different groups have similar embryonic stages early on, more similar early, less similar late in embryology. Late, coming closer to hatching or being born, there has been more development, more specialization. So the morphological difference is greater, right? But going back in embryonic development, the stages are more and more similar. If we go all the way back, how far back can we go? Let's stick with these vertebrates, okay? How far back can we go? What is the first stage of embryonic development? It's another question. The what? The zygote, fertilized egg. Before the fertilized egg, you have an egg, which is not an individual, new individual, it belongs to the mother. And you have sperm, which belongs to the father or to the man. So unless and until there's fertilization, there's no new individual, right? Those cells belong to organs of the parents, potential parents. Then if there is fertilization, when there is fertilization, then we have the beginning of a new individual. So the earliest embryonic stage is the zygote, which is unspecialized, and it's a single cell, and it's round, spherical, and we look at the zygote of a fish, and we look at the zygote of a salamander, or we look at the zygote of a bird, or the zygote of a cow, or a human, what are they going to look like? Spherical, round cell, kind of transparent to the microscope, to the light microscope, unless we stain it. And the only difference, if we detect any difference at all, is going to be just difference in size. And I'm told that a cow egg, for example, or a zygote, you can actually see with the naked eye barely. A cow egg, which is maybe 10 or 20 times larger than a human egg, human ovum, okay? But for the rest, it's just a sphere, a round ball, all right? And they all look alike, except for perhaps size, which more or less will correlate to the size of the animal itself. And even the mora, which is the second stage, and the blastocysts, they're pretty much going to look very, very similar. But they are very different species, because a turtle looks very different from a fish, which looks very different from a rabbit, which looks very different from a human. Even just newborn or newly hatched, right? So that's what that's saying. Because of this, again, the development of the individual is called the ontology, all right? Or ontogeny, ontogeny better, because onto, individual, geny is, can I have it? Yeah, ontogeny recapitulates phylogeny. It's on the sheet. Ontos is the origin of the individual, or the individual. Geny, genesis, is a reference to origin. Phylogeny, you should be able to tell me now already what phylogeny is. The geny part is a reference to the origin, right? Of the phylum, phylogeny, right? So the origin of the group as a whole, which includes many species, many different species, many ontos, right? Okay, so ontogeny and phylogeny, the origin of the individual, the origin of the group as a whole. And there was this old saying, in fact, when I was studying biology, when I was being taught biology in high school in the 1960s in Mexico City, the standard, what the professor kept saying, ontogeny recapitulates phylogeny. Ontogeny recapitulates phylogeny. I have it on your sheet there. What does that mean? It was thought that because the embryos look more similar to each other, different species look more similar to each other early in embryology than later in embryology. And because there were these characteristics that were common among all species, even if those characteristics later did not develop into actual organs. For example, the gill slits. I'm going to talk about the gill slits a little bit further down. For example, in mammals, we don't use gills, right? But there's an embryonic stage where we have the gill slits, the actual little openings on the throat region. It was thought that ontogeny, the development of the individual, recapitulated. In other words, relived the phylogeny, meaning the origin of the whole group of all the mammals. So that, let's say, from fertilization to birth, the 9 months of the human development, human embryonic development, think of human pregnancy from conception to birth, 9 months, right? That in those 9 months, each one of us would recapitulate, would relive the origin of our species as a whole, okay? Of the primitive hominids, of the ancestral, like for example, we would relive, we would start, say, as a fish egg, a fish zygote. And then by the time we get to the morula, maybe we're already the amphibian. And by the time we get to the blastocyst, we're already the reptile. Then by the time we implant, then we're the bird. So, you know, that's kind of putting it simplistically, but that's what that meant. A little phrase, a catchphrase, ontogeny recapitulates phylogeny, was implying that during the embryonic development of any species, they were reliving, the different embryonic stages were reliving the evolutionary stages of the group as a whole. Whether that group was mammals or vertebrates. You follow me? All right. It is now proven that that, strictly speaking, is not true. Ontogeny does not recapitulate phylogeny. Okay? Not in the strict sense. If anything, we can talk about that in particular organs or structures a little bit, especially when we have what is known as vestigial organs that I'll address in the next slide. But so strictly speaking, we don't jump from species to species during embryonic development. We're always the same species. It's just that that species is becoming more and more specialized. That individual is becoming more and more specialized. And so more distinct structures are developing and coming forth. But we remain the same species from ontos, from the beginning, from the genesis, from the conception, all right, from the fertilization. But particular structures do appear at some point in development, and typically those are vestigial structures that, again, what they're pointing is to a common ancestor. So if the same structures are appearing in different groups, for example, the gill slits in mammals, in birds, in reptiles, amphibians, and fish, those gill slits are appearing in all those different groups. That is inferring that all these different groups had a common ancestor that had those gill slits where we inherited from them. Okay? And that's what that means. So in that sense, there is ontogeny, there is phylogeny. It doesn't really capitulate the ontogeny, the origin and development of the individual does not recapitulate the origin and development of the group as a whole, but individual structures do point to common ancestry. They do point to common ancestry. Otherwise, there's no logical explanation for those structures to be there if they don't really have a function in that group today. Again, gill slits or tails or the remnant of tails in us
okay, which is the coccyx, right?
Okay, so that leads me, let me see if I had anything else there. Right, so that leads me into what we call vestigial structures. Now, it's 11:20, and I'm going to take a break at this point. And yeah, okay, let's break a little bit. It's going to be a continuation of the argument a little bit more, and then eventually we'll finish up with biogeography and molecular evidence. We're about a little more than halfway through. Okay, I'm going to pause the recording now for the break for about 15 minutes, more or less, a little bit after 11:30, we'll be back. So if anyone is following the video, just in case, pause recording. Okay, welcome back. So here we go to the second part of this lecture on the evidence of evolution, the material evidence that we see around us for evolution. Now I'm going to delve a little bit more into these vestigial structures, all right, vestigial structures that we saw typically in embryonic stage, but also as adults. So in the adult body, for example, we have several vestigial structures. The most noted ones are tonsils, the appendix, and the coccyx. Okay, the tonsils, or the wisdom teeth that sometimes do not come out, or they go horizontal. One of mine, one of the four, started despuntando. How do you say that in English? I noticed with a toothbrush that there was a hole in the gum at one point. I said, what's that hole about? And it turns out that one of the four wisdom teeth was beginning to sprout or whatever, coming out, but it didn't come out all the way. It was just partial. It's called a partial, right? Okay, but they left a hole there, and then that hole, of course, accumulated food and all that, so it started getting a cavity, and so it had to be pulled out. Surgery and all that. I had to go to the orthodontist. And the idea was, well, to pull out 1, 2, 3, or 4. Because, and when she showed me the photograph of the X-rays, they're all horizontal, right? Which I guess is very typical. They shift, which the gums is a muscle, and it shifts around even during the day. The teeth shift around a little bit. You notice if you floss, which you should floss. Sometimes it's tougher and sometimes it's lighter, easier to get in with the floss, right? Because the teeth, again, it's another dynamic system and they shift a little bit. Anyway, it's impressive to see those tonsils horizontal like that, right? But they are reminiscent of ancestor that was probably a herbivore, which those tonsils were functional for grinding. Right, they were used for grinding. Our ancestors had more molars, like the cows, horses, all these animals that are mammals but are herbivores. They feed grass or plant material. It needs to be chewed a lot because we can't really digest cellulose. We don't have the cellulase to digest cellulose. So whatever nourishment has to be gotten out by the grinding effect, the actual grinding. Anyway, all this to say that tonsils today for us are non-functional generally, but they're still there. How do we justify? It was not just by whim that those tonsils were placed in us and left there just to give orthodontists a livelihood, no? And so they point to some kind of common ancestry where the molars were functional in some ancestor. The same with the appendix. In fact, the speculation is that the tonsils and the appendix are somehow related in the sense that the appendix may point to a cecum or a bag, like a second or an extra stomach that the ruminants have. The ruminants are the animals that are mammals that are herbivores, precisely like cattle, that have to chew the cud and then they have to leave it in the rumen in part of the stomach for it to ferment and try to get more nutrition out of it. All right, it's like fermenting hay or something like that. When it breaks down by fermentation, the animal is able to get more nutrition out of that hay. And so the speculation is that the appendix is a degenerate bag, a degenerate, what used to be a functional other chamber of the stomach in some kind of ancestor, which that chamber, that extra stomach chamber is still functional in cattle today, right? So we have a common ancestry with cattle way back somewhere. Similar to the coccyx for a different reason, different functionality. The coccyx, otherwise known as the tailbone, we don't know we have them until we fall on our behind, and then we break the little tailbone, and then we really know we have it. And you cannot put a cast on it. You just have to walk slowly and gently until it repairs on its own, and it will with a little patience. But why do we have that little tailbone down there? Why do we have a remnant of a tail, which are what, 3 or 4 fused caudal vertebrae, right? Tail vertebrae. What are they, about 4, I think, or 5? I don't know. But they're fused. They form one single structure with the pelvis, more or less. But it doesn't really have a function other than causing pain when we fall on it. So it's a remnant, right? It's a remnant. It's a vestige of some ancestor that had a functional tail. And the typical tail is at least as long as the rest of the body, but it's in the opposite direction of the rest of the body. And if you think about it, the tail and the body kind of pivot on the pelvis. So it's a balancing organ mostly. It's balancing for running, for the tetrapods, right? It's a balance, the tail itself, a functional tail, which later, secondarily, for the primates, in other words, the tetrapods that climb trees, it serves almost as a 5th leg for grasping and hanging from it. Okay? But we can see contemporary mammals that have functional tails. Whereas, and they're articulated and so forth, they're not fused like our coccyx. So that points to some kind of common ancestry with these other mammals that have functional tails, because our tail is non-functional. And the other primates also have the tailbone, but it's non-functional. I'm talking about the orangutan, the gorilla, the chimpanzee. But then what we call lesser monkeys or other monkeys do have functional tails. So there's some kind of relatedness there, right? Similar, since we're around the area of the pelvis and the coccyx and the mid-region, the actual pelvis or degenerate pelvic bones remnants are there in the skeleton of whales, cetaceans. Cetaceans are the whales, the dolphins, the orcas, okay? These are marine mammals. The mammals, because they have lungs, they don't have gills. They also have hairs, few and thick, but they have some hair around the eyes, they have some hair around the nipples, which the nipples are underneath the pectoral fin here, okay? And by the way, a calf whale will drink several hundred liters of milk daily. Okay, it's massive. It fits the size. They grow fairly fast too, but they're mammals, so they have to have mammary glands. And they also have these remnants of pelvic bones. They have pelvic rudiments, vestigial, all right? They have rudimentary structures or organs. What does a whale do with a pelvic bone or a dolphin or, okay? It's not needed in the occurring function. And that's why it's thought that the marine adaptation, the aquatic adaptation, is a secondary adaptation. That their ancestors were tetrapods which migrated back into the oceans. at which point the forward limbs became flippers eventually with evolution, and the hind limbs were lost, degenerate, they were selected out because they were disadvantaged. They were essentially a drag, literally a drag on the swim. But the rudiments of the pelvic bone remained because they haven't been selected out yet. In other words, it doesn't, the moment these pelvic rudiments, these vestigial pelvic bones become a burden to the whale or the dolphin, they're going to be selected out because they will make that whale or dolphin weaker. All right. And in fact, I know that I've heard some people are born without the appendix. A few people are born without the appendix and they do fine. And it could be that eventually those people become so successful in reproduction that, of course, children of people without appendix are likely not to have an appendix, right? Not because there was an appendectomy, simply they were born without it. But typically we don't know we don't have an appendix. And so how are you going to find a mate who doesn't know she doesn't have an appendix either? In other words, we don't select for appendix when we fall in love. Right? But it's there. Okay, so these vestigial organs, they point to some common ancestry where these organs were functional. This in adults. Oh, the other one is a snake, also the snake, which it's obvious that snakes by definition don't have any legs, right? But they do have a pelvis, or the rudimentary of a pelvis. And so what's the need for that pelvis if it's not hinging any limbs? Hmm? Let's look at a snake skeleton for a moment. And that's what you can tell that the actual tail begins. Find one that's a little more illustrative. No. Well, maybe if I put snake pelvis. See what happens. So it's going to be degenerate, but generally you can tell that's where the actual tail begins, because otherwise, how do you tell the tail on a snake? No, it doesn't begin after the neck. Okay, after the neck begins the main part of the body. And then after the anus begins the tail. And that's, by the way, when the scales go to two, they will have a single scale, right, on the ventral side, on the belly side, they will have a single scale at the bottom till the anus. The anus side, the last single scale is the opening to the anus, and then beyond that they have two scales, and that's formally the tail of the snake. All right, but well, here's a diagram of the rudiment magnified many times. Obviously, here's the forward. This is the forward part of the ribs, and then the tail begins here. This is a rudiment of a hip with a little spur. See how the ribs become much smaller into the tail region, but they have the rudimentary of a rib, of a pelvis. I guess this one. Let's see if I can magnify a little bit. Okay, these extra little bones here are the rudimentary of the pelvis, because these are all ribs. And then that's the tail ribs here. There's a little bit of change in the anatomy there. It's not very well seen, but anyway, there's a rudimentary of the pelvis, which means that the snake anatomy is a secondary from a legless, from an ancestor tetrapod that degenerated and lost in the legs for selection. And now they are legless. So they have a common ancestry with lizards. In fact, lizards, by what is known as convergent evolution, Some lizards eventually developed into legless lizards, but they're true lizards, which are not snakes. Okay. It's probably going to come out too big. So let's tone it down. But these are legless lizards, which are totally legless, but they're lizards and not snakes. They have some characteristics that make them lizards and not snakes. But that's called convergent evolution. Okay, let's look at the gill slits for a moment, a little closer, because it's also interesting that some of these vestigial structures may later acquire secondary functionality. Okay, so here's a little diagram again of fish, reptile, bird, and mammal. Is pointing to the tail, which we talked about already, functional in the other classes and orders, but not in the human, not in the mammals. However, or human, because other mammals do have tail. But I want to focus on the gill slits because the slit itself is just the opening. They may or may not develop a gill behind it, underneath the slit, but the slit itself is the opening, okay? They're also known as pharyngeal slits or pharyngeal pouches. So it's a sophisticated way to say the same, pharyngeal pouches or gill slits. But you notice here is an embryo, human embryo, and here is the fetus more developed. You can see that these different regions of the pharyngeal pouches or gill slits secondarily become different functional structures on the human. For example, some of them, the upper ones, become part of the jaw, the lower jaw. Others migrate into the inner ear, the bones of the inner ear, and others migrate down to the cartilage that surrounds the vocal cords, the trachea. You can, if we swallow, you hold here and swallow, you feel it going up and down, right? And these are secondary adaptations to the original gill slits, which in our ancestors had a different function. And so this could be a reason why these gill slits have not been selected out in mammals, is because they have acquired a secondary adaptation that is functional. And these are developmental, or these are part of the body plan. This is known as homeotic genes, which I'll cover later when we get to the molecular evidence. The HOX, or the homeotic box, or developmental genes that have to do with the body plan early on, okay, as the body is differentiating into different regions. So in us, the gill slits do not further develop into functional gills as they do in fish, but they do develop into secondary adaptations, which are functional, like our lower jaw, the inner ear bones, and even the cartilage around the trachea. Okay, different line of evidence for evolution. Big picture, biodiversity, or what is known as biogeography. In other words, looking at geographical regions, large geographical regions, biomes, and their particular fauna, or flora and fauna. And seeing, well, that these related species live in very different parts of the world today. And a classical example again is the different camelids, which, by the way, one hump makes a dromedary, two humps makes a camel, right? Generally. And that's in the dromedary typically in Africa, Northern Africa, the camel in Asia, whereas the llama and related species in South America. no current land bridge, but an ancestral land bridge through the Bering Straits, Siberia, and Alaska. Okay, and there are actually at least 4 different species of llamas in South America. If you've ever been down there or seen some movies and clips, you have the llama, you have the guanaco, the vicuña, and the alpaca. These are different types of different species. Further development once they got down to South America. But they're all related, distantly related to the camelids of, they're all camelids of Africa and Asia. Okay, and they're separated by entire continents. So that's that biogeography. That can be explained because these diverged before there was what is known as continental drift and plate tectonics. Okay, so if we go back to 250 million years ago, or around 225 million years ago, all right, 250 million, we see that there was one large mass. This is the theory that there was one large mass called Pangaea. Again, the name is mostly from Greek. Gaia or Gaia is a reference to Earth. That's also how we, from where we get geographic, and Gaia and Gaia, they all have the common Greek root of Earth. And Pan, meaning all or many. So all the Earths, all the crust put together in one supercontinent. Pangaea has been known as a supercontinent, okay, which fragmented and slowly started drifting. The first big drift was between north and south to what it was known as Gondwana or Gondwanaland, which would be basically the southern fragment of the crust, and whereas the northern is known as Laurasia. Further fragmentation and pulling apart. Again, you can think of these as rafts or floaters on top of the molten lava, the molten magma that is moving and circulating. We'll see this in greater detail when we get to the summer. But it's, these rafts are sliding and slipping generally away from each other, from one concentrated origin here, all right, as a single crust, fragmenting and moving away into the 6 or 7 continents that we know, but still Europe and Asia together, so that this also has a single name, Eurasia. I don't know if you've ever seen that name, Eurasia. Europe and Asia as a single large continent. North and South America breaking off, Africa also, and India, which is really not considered a continent as such, but a subcontinent, mostly because of size. And then Australia and Antarctica not fully separated, to where we get today, where we have the 6 continents, North and South America, Europe, Asia, Africa, Australia, Antarctica, and then the Indian subcontinent, which peeled off originally from Africa. So you can see here, Pangaea, all right, segment of Africa and Antarctica, if you will. And this floater started migrating up fairly fast, up north, and crashed into Eurasia, and is still pushing into Eurasia, into Asia, and is buckling between Asia and India, is buckling up, and that's the Himalayan Cordillera, the Himalayan mountains, the largest mountain range in the world, right? Something similar is happening in North America, pushing against the Pacific Ocean and a submerged plate, if you will, part of the crust, and That buckling is causing the North American, the Rocky Mountain range, which then when it goes into Mexico is known as the Sierra Madre Occidental, right? The mountain range on the west, which is much more massive than the one on the east. Similar to comparing the Rocky Mountains with the Appalachians, for example, which are much smaller. And then when you get into South America, you have a similar phenomenon, independent of the North America, because South America is a plate by itself. It's another tectonic plate, but still pushing into the Southern Pacific at this point and causing what? The Andes, the Andes region, the Andes range, mountain range, okay? So all these large mountain ranges are basically buckling up of the crust, pushing up, because of the slowly but surely movement of these crusts, these rafts, these plates pushing against each other. In opposite areas, there is an upwelling of land, of magma, if you will, which cools and solidifies, and then it spreads out. Typically, it's happening in the middle of the Atlantic, and it's called the Mid-Atlantic Ridge, and it causes what is known as seafloor spreading, and that's what's causing the continents to come apart, meaning Europe apart from North America and Africa apart from South America, because of seafloor spreading. Is the opposite phenomenon of those convergent currents that are coming up and are pushing the continents apart from each other in the Atlantic, along the middle of the Atlantic. And that mountain range, known as the Mid-Atlantic Ridge, is huge, humongous, much larger than the Himalayas, which is the largest one we know on land. Okay, we'll get to that one later in the program in the summertime. But this has caused this biogeography diversity. Kind of, you can see broad bands here of the different biomes. There are about a dozen biomes here, and you can see that generally they coincide, but they go across the Atlantic on this side and the Pacific on the other side. But yet these are similar. There's tundra in Siberia, northern part of Eurasia, okay? This would be basically Russia down here. And there is a tundra in the northern part of Alaska and Canada. Then further down, you get into that taiga, or the coniferous forests. This is the huge tracts of pine tree forest, both in the North American plate and the Eurasian plate. And the bands more or less match. Further down, you get into the temperate region with temperate deciduous forest, so on and so forth. The tropical rainforest further down, you have it in Central and South America, you have it in Southeast Asia and India, and you have it in equatorial Africa. Okay, so there's a general matching here of the vegetation in different countries, in different geographical regions that are totally isolated from each other today by vast expanses of water, the oceans, which is salt water to boot, all right? And so this migration, this dispersal of related species had to happen before the break, basically, before when it was all Pangaea, because this was a mere 225 million years ago. This was all populated by plants and animals, okay, ancestors. And so this biogeography that we have and the biodiversity and similarities between different continents of the flora and the fauna of different continents is also pointing to a common origin of the species when these plates were closer together to each other. This slide just makes the point with regards to plants also. So this happened with plants. In fact, it happened with plants before it happened with animals, because they're older, right? And here I just pull out some fossil palm ancestors. There's no doubt that this is a fossil palm frond, a palm leaf,
All right, you can see the palmate veins on it. It's very evidently a fossil palm. This is a palm trunk, very, very characteristic of the palms as they shed their fronds periodically. They get these scars, this very typical pattern. Here's another type of ancestral palm frond, all right, no longer living today by definition. They're fossils, they're extinct. But we have related living palms today in all the different continents of the world, more or less around the tropical and subtropical region, because palms have a characteristic that they don't tolerate much cold. So we are pretty much in the northern part, we meaning Southeast Florida here, are the northernmost region for the palms. You're not going to find palms even in northern Florida. It's difficult to find them. The exception is, for example, Ireland, where because they get the breeze from the Gulf Stream, that after going through Cape Hatteras there in the North Carolina, the Gulf Stream, which is warm water from the Gulf of Mexico, right? Salt water is like a current, moves out and crosses the North Atlantic Ocean and goes to land over there in Ireland, across the North Atlantic, but it's taking its relatively warm water and humid air on top of it. And that's why in Ireland it's very rainy and misty and it's relatively warm. And it's very rare to have snow in Ireland. It rather has more temperate climate than even in Great Britain or its equivalent in the continental part. Think of Sweden and the Scandinavian countries that are very cold and they have significant snow, right, in the winter, simply because the Gulf Stream is maintaining Ireland artificially or not by geography, but the climate is making it warmer than it's supposed to be by geography. Anyway, palms are typically from the tropics and the subtropics, and we find them in all continents, and yet they're terrestrial. You know, how did they get there? It's pointing to a common ancestor, which would be these fossils. Different line of evidence. We're going to look at the molecular evidence, which is actually the strongest one now, the most comprehensive and detailed evidence for the fact of evolution. And so we talk about homology. Homology, which is degree of similarity, okay? For example, when we talk about anatomical or morphological homology, remember, with the arms and the four limbs, this was homology, right? They are homologous structures, meaning that they have a common origin, but they have a different function today. It could be slightly different or it could be very, very different, but they have a common origin. That's what the homo means, it's the common origin. Okay, so let's look at the molecular level, which is as detailed as we can get with life, with organic life. This is percentage homology between the human and other species, some more closely related than others, on hemoglobin, all right? In other words, the monkey has hemoglobin, mouse, chicken, frogs, lamprey, because they're all vertebrates, and they have some kind of a molecule that they'll have a closed circulatory system. And so they're going to have some kind of blood cells that transport oxygen. So they're all vertebrates, meaning that they all have a closed circulatory system. Unlike insects, for example, and other arthropods that have an open circulatory system, meaning that their blood just squishes through the tissue more or less, okay? But no, we have a closed circulatory system in vessels. So within those vessels are different types of cells that have different types of function. The RBCs, the red blood cells, are in charge of carrying the oxygen and then also getting rid of CO2, right? So they're in charge of gas exchange from the tissue out to the environment through the lungs. So in humans, we have hemoglobin, which is made up of 4 myoglobin molecules. Don't worry about it, too much detail. Basically, it's a polypeptide, it's a protein. Think of hemoglobin as a type of protein. In other words, it's coded out of DNA, comes from a DNA sequence. Okay, percentage homology. Of course, for all humans, it's 100%. Our hemoglobin is compatible with other human hemoglobin. We have 100% compatibility of our hemoglobin generally. Now, when we look at the species of monkeys, why rhesus monkey? Anybody know where the rhesus monkey becoming important in clinical trials and for blood transfusion?
Genetically more similar to humans?
Yes, and they were just used for experimental purposes to obtain blood and to do blood experiments and so forth. You heard of the Rh factor? Okay, Rh factor comes from the rhesus monkey, Rh, there it is, Rh. Okay, so the rhesus monkey has in their RBCs, they have another protein, aside from the proteins that make up the ABO factors, the blood type, positive, A type or B type or AB type or O type, right? Those are types. Those are different proteins on the surface of the RBC. Aside from that, those types, for that set of proteins, there's another set of proteins that we either have or not have. And it's very homologous, that protein is very homologous to the rhesus hemoglobin RBC protein on the surface, all right? And so if we have that protein, then we are Rh positive. If we don't have that particular protein, we're Rh negative, okay? Now, right now I'm just kind of thinking out loud. I don't know that there is a particular function other than causing a blue baby in the second or third pregnancy of an Rh factor incompatibility, okay? But I don't know that there is necessarily a function to that protein, to that polypeptide on the surface of the RBC. Does anyone know? There's no known function, right? In other words, Rh positive and Rh negative, I don't even know what's the distribution in the population. Do you know by any chance? Is it 50-50 more or less? Or?
It's more positive than negative.
More positive,
Yeah.
Significantly more, like
Yes,
40-60 or 30-70, more, significantly more positive, statistically. Okay, so, but it hasn't been selected out. So it means that it could be that the Rh factor is a vestigial protein that is just hanging around from a common ancestor with the rhesus and with other monkeys, all right? Anyway, my point is that, it's a sideline really, but the Rh factor on the blood type comes from the rhesus monkey. It's a protein that the rhesus has that we either have or not. If we do, it makes us positive. If we don't, it makes us negative. But it is important compatibility-wise because we do develop the antibodies and we would go into an immune reaction if we're negative and get positive blood or vice versa. Well, no, if we're, let's see.
Negative is the universal donor.
Right, so negative, right. Negative means we don't have it. So we can receive Rh positive. But Rh positive, no. We can do universal donor, right, universal donor, but not recipient. In other words, I'm O negative. And if we get positive blood, we go into an immune reaction because that protein looks like a foreign creature to me, whereas an O positive person has no problem with the protein. Has no problem without the protein either, so they can receive. That's why O negative is universal donor, because they can receive no protein, doesn't affect them. But the no protein people, the protein will affect us, all right? Separate from the ABO typing of the blood. Anyway, our hemoglobin, human hemoglobin, is 95% compatible with rhesus hemoglobin. Maybe that's why it was used for experimental purpose, okay? But we're 87% with the mouse, mus musculus, all right? Which is the poor common lab mouse that is breeding all the time, because we're 87% just on the hemoglobin. On other genes, it may be more. Other genes, it may be less, all right? But on the hemoglobin, which is pretty a universal protein for mammals, 87 with the mouse. And morphologically, for the rest of the body, we're pretty dissimilar to the mouse, right? In the rest of the anatomy. The chicken, which is not even a mammal, we're 69%, the hemoglobin, chicken hemoglobin. Remember, I used chicken hemoglobin in in my genetics research at Purdue, because unlike the mammal hemoglobin, where the mature RBC does what? The mature RBC dishes out the nucleus, right? So it's enucleated. That's why they last little. They have to be replaced. The spleen, right, eats it up and is replaced all the time by the bone marrow. But that's in mammals. The birds, their RBCs are nucleated. And because there's so many chickens killed and the blood is harvested and sold to scientific labs, it's a great source of vertebrate nuclei. All right, for doing genetic research and genomic research. I was doing DNA research. And so we would just get chicken blood by the bags from some kind of an outfit. And that was an immense source of nuclei, of vertebrate nuclei. Okay. So with birds, with the chickens, we are 69% compatible, our hemoglobin. Frogs, 54% compatible. Lamprey, what's a lamprey? Anybody? These are part of what is known as jawless fish. They're primitive. They are more primitive than the jawed fish. Like, for example, definitely sharks are jawed fish, right? Very much so. But also other fish, osteichthyes, the ones that we catch when we fish or we eat when we have fish. Those typically are fish that have jaws. But these are more primitive. Some are lampreys, some are hagfish. They tend to have a circular disc that attaches, they're parasitic, they're external parasites, and they latch onto other fish and chew them up and are parasitic. But we're 14% compatible with the lamprey, which is pretty far removed. You know, just about the only thing we have in compatibility with the lamprey is that they're fish, therefore they're vertebrates, so we have a vertebral column like they do. But that's about it. You know, they have gills, we have lungs, they're aquatic, we're terrestrial, et cetera, et cetera. So this is the percentage homology, and it's looking at a hemoglobin, which I told you is a protein, but this is the result of a DNA sequence. If there's a protein sequence of amino acids, there's going to be a DNA sequence, which is the code for that sequence of amino acids. So when we say protein homology, we can just as well say DNA homology. We can translate this into DNA homology between the human and the lamprey and every other creature in between at the level of the code, the genetic code for the hemoglobin. You follow me? Okay. So in a sense, this is looking at it a little more functionally, if you will, but the DNA would be looking at it a little more structurally, because the code remains in the nucleus. It gets translated in the cytoplasm into a protein. Emma?
The children nowadays, they can alter the sex of a baby.
Well, yes and no, but it takes a lot of genetic engineering and typically would involve in vitro fertilization and something like that. All right. We'll cover sex and gender later in several times, but we'll start covering it in the spring when we look at the beginning of life issues, and then also in the healthcare course, which is the last one in the second fall. All right, which is what the other cohort is taking now. All right, we're going to go deepest yet for a moment. So bear with me for a little bit. I want to look at this DNA sequence that I told you about, and the Hox genes, which is a short for homeotic box. All right, here's the HO and here's the X. Hox stands for homeotic box genes. These homeotic box genes are basically developmental genes of the body plan. All right. They establish the body plan of an embryo from the head to the tail of any species. And so they are very conserved, as we say. They have a lot of homology because they are developmental genes early on, and they establish not only where the head is going to be, what end of the embryo is going to be the head, and what end is going to be the tail. That makes a big difference, right, developmentally, but also every other part in between. So the mid part between the head and the tail is everything else in the body. The mid region, all the vital organs, most of the vital organs are contained in between the head and the tail. And so these developmental genes, this Hox, the homeotic box, is what establishes that pattern, okay, by segments. So that there's for example, in the insects or the arthropods in general, there's going to be a head, there's going to be a thorax, and there's going to be an abdomen. And each one of those three regions will have major functions, vital functions in the adult. All that gets established in the embryo, and you can see analogically, here is the Hox plan for the baby human, for the human embryo, human fetus, beginning with the head region, including the cephalization of the brain, the vertebral column, all the way down to the coccyx region, which will be very tiny, but the significant part will be the head and the mid region, which is going to contain every other vital organ. So these Hox genes are developmental genes. They occur in every animal, and they set up this plan, early on, that will eventually differentiate into the different body parts. And therefore, they are highly conserved in the big picture. In other words, where the head is going to be toward the front end of the embryo, whereas the tail is going to be at the opposite end of the head, and so forth. Okay? So these sequences are fairly well conserved, and they're used for studying developmental biology and comparative developmental biology at the molecular level. So we're not just going with external structures or even functions or behavior. We're going down to the molecular level, which is the most sophisticated one. So follow this argument a little bit, simply because Meyer speaks there, toward the end of the chapter, about how to come about new genes, how to get a new genotype, okay? How to generate new genes. And the theory is that pretty much is by a repeat, by a tandem repeat. A tandem repeat means it's a duplication of the gene that is adjacent to the original. And that's what is called tandem repeat. It's like wagons on a train. Adjacent wagons are in tandem. They're locked into one another, okay? And some wagons on the train that are not adjacent, but some have to be adjacent to make the train. So we start with a hypothetical ancestral gene that is a Hox gene, or it's a Hox-like. In other words, is going to determine this region. It's kind of small up there, but let's see if I can try to focus in on this area. Here we go. Okay. Too much. Okay. See, ancestral Hox-like gene. Can you read that? Mm-hmm. Yeah. Okay. Good. Here's the DNA sequence. You see the double helix represented there, the spiral, and the right. So here's a region, a coding region of the DNA. All right. We'll call that a gene. It's a coding region. Means that it codes for some protein or some set of proteins. And these are Hox-like. In other words, this is a region that is going to determine the general body plan of this ancestral organism. At some point, that gets duplicated. It gets duplicated by chance. There is frankly a mistake here. There's an error. The reading happened twice. It's like the photocopier photocopied the same page twice and sent it out in the package, but you had automatic clipping, what do you call that, stapling. So when you get the whole package of 200 pages, there's actually 201 pages because page 57 got duplicated twice, got duplicated with the machine by an error from the machine, and they all got clamped together. So you have an extra page in there that is a duplicate, and it's a tandem duplicate, all right? See what I'm saying? So that happens in the reading mechanism, in the replication mechanism of DNA, which we'll cover later. But basically, this can happen by mistake, but it latches on. If this develops a secondary functionality, it will stay, it will not be selected out. Most mutations are neutral. They don't really have an effect. They just make up more of the bulk of the DNA of the genome. Most mutations are neutral. They don't have an effect. The ones that are non-neutral tend to be deleterious. In other words, they don't abode for something good. It could be an excess. This could read too much of the same protein. It's an excess. So that individual is going to be selected out, meaning it's not going to survive. It's got too much hemoglobin. It's got too much of that particular protein. It's not going to make it to maturity, to reproductive maturity. Guess what? It just got selected out. Or every now and then, very rarely, the duplication, the mistake, the random mistake, the mutation happens to be beneficial. Actually, so let's say there is a duplication of the hemoglobin gene, and I am living in a high mountain where there is less oxygen. Better to have more hemoglobin where I have less oxygen, right? Available. And so it could be an evolutionary advantage. It could be an environmental advantage or a survival advantage, and therefore it will stay, not be selected out. All right? And that's how, by chance, mutation, a gene may shift functions. So with some time, what can happen is that this gene can develop a somewhat different function, the second, the tandem. That's where you get orthologous and paralogous. Remember, he talked about orthologous is the original and paralogous is the adapted gene, which develops a secondary function. Eventually, with time and additional duplications, you get related functions. And so this is a possibility for the whole homeo box developing, the whole homeotic box developing by these tandem repeats that eventually develop somewhat different functions. Then there was a point of drastic divergence here, okay? The drastic divergence is that some of these creatures stayed in the ocean and remain fairly primitive. They did not need bilaterality because they can move essentially in any direction in the water column. They can move up, down, east, west, north, south, around, and twirl. So they could maintain a radial symmetry like the jellyfish or the sea anemone or the polyps of a coral. They have radial symmetry. However, if some of these ancestors migrated into land, then now they have to crawl around. So it's more functional and it's more adaptive to have a front and a rear to move unidirectional, which is not that much needed in a column of water worms surrounded by more or less equal medium all around. All right. So moving into land could be possibly this divide here, where now moving in a particular direction has a functional advantage, has an evolutionary advantage. And so that that homobox will continue to develop, favoring bilaterality and an anterior-posterior body plan. Anterior-posterior body plan, which is different from a radial body plan, right? Compare again a jellyfish, which is more or less symmetric radially, as opposed to a worm, some kind of primitive worm that is crawling, moving forward. And while they're crawling, that evolution is also going to favor if the sensory, the external sensory perceptors are toward the anterior end, what will eventually be called the head. Whereas the trailing end, since this creature is moving this way, generally forward, and that's where it's foraging and scavenging and trying to find its food and so forth, then the trailing end is going to have less and less sensory systems, right? maybe eventually just down to tact, but the other 4 senses will concentrate toward the head. And internally, there's going to be a correspondence, an internal correspondence to those external senses in the head, which is a cephalization. In other words, the receptors of those, where those senses are going to connect internally, which is in a centralized neuronal place where this information, the sensory information, can be processed, which is cephalization. It's the beginning of a brain. You follow? And so that's all body plan, which will be favored by moving on land. Moving on land, which on land we cannot move in all directions at the same time, right? We typically have to crawl or some variation of crawling along the surface. Okay, so that could be a common ancestor, which is bilateral now because we're terrestrial here, okay? This bilateral ancestor is terrestrial, and, whoops. When we follow lines of divergence, this creature could be a node of a breaking point between these creatures and these other creatures. There will be continuous development because there's an Adamic state going on here with the homeobox over long periods of time, where if there is duplication, then by definition, you're adding more and more carts to that wagons to the train. I don't know if you've ever gotten caught by the Hialeah train, if you're going north-south on Lejeune Road, okay? But if it's right around rush hour time in the morning, and then it's, sometimes it's rush hour in the evening, or sometimes it could be 10, 11 o'clock at night, but there's the train and you sit there and you count wagons. So it's duplicates and duplicates. But then over time, some of these duplicates can begin to specialize, again, by random mutations that have a positive selection, have an added advantage to the particular creature, wherever it is that they're living in, whatever environment they're living. And so that homobox is becoming more and more specialized, okay? But there's going to be remnants, there's going to be homology, there's going to be percentage homology. So for example, in this one here, where he took it, the diagram took it all the way to the tetrapods, meaning the 4-legged vertebrates. This excludes the fish, but all the other 4 vertebrates are included. What are the other 4 classes of vertebrates? 4 classes of vertebrates: amphibians, reptiles, birds, and mammals, right? So the only vertebrate that is excluded from here is the fish, which is not a tetrapod, but these are tetrapod, meaning that these live at least for some time on land. Look at the percentage homology. This is today looking at birds, amphibians, reptiles, and mammals of the homobox, of the Hox genes, all right? There's 100% homology on this one, on this exon, if this is a coding region, 100% homology here, 75% homology, 75, 50% homology. You follow me? And then it varies between the different classes, 100% on all 4, 100% between bird and mammal, but only 50% with amphibian and reptile, as vertebrates as a whole, okay? So it depends on which class we're looking at, but there is percentage homology. By looking at this homology, we can see which 2 groups are more related to each other, okay? At least on this, on the Hox gene, tends to be more relationship between the bird and the mammal, especially in this region, whereas more relationship between amphibian and reptile in this region. You see it? There's more homology here than here, but yet there's more homology here than here. So these regions are more homologous between birds and mammals, whereas these other regions are more homologous between amphibians and reptiles. The common ancestor of all these four had to have somehow all these regions, okay, which later developed further into the four different classes of mammals that we call the tetrapods today, tetrapod vertebrates. All this to say that when we look at proteins, which is to say when we look at DNA, we can determine percentage homology between the different molecules. And by doing that, we can put together these maps so that we can determine common ancestry. Okay. Here I was just explaining the homobox, but notice the homology here. This is the fly. It happens to be, I think it's, yeah, Drosophila fly, which is used a lot in experimentation, especially the early part of last century. This is the ancestral gene here in white. Okay. Drosophila, one single homobox. We have 1, 2, 3, 4 homoboxes. More sophisticated because we're talking about a mammal as opposed to an insect. But the general body plan, look at the percentage homology. It's amazing that we have this much percentage homology with the fly. All right, look at that one. It's practically identical across. These are exons. These are coding regions of the DNA. That's practically identical there. Look at that. Okay, and this one too. But yet this region is not in the ancestor, whereas this region is in the ancestor. So this had to be a development further on. Okay, at the end of the day, what we can do is these maps. This is the actual DNA sequence. Now we're going behind the protein, before the protein, all right? The protein is a product of transcription and translation. Here we have the actual gene sequence, the code, the DNA code, which is just represented by one base. Remember, the DNA is a twisted ladder which has base pairing, and I just give you the base pairing here. C always pairs with G, and A always pairs with T. They correspond to cytosine, guanine, adenine, and thymine. Don't worry about it. They're rings, single rings and double rings biochemically. We'll look at them in detail later on. But basically, they form the steps or the rungs of the ladder. Okay? And that's where the DNA code, that's the actual code there is in the sequence, just like a sequence of letters on a book will tell us whether it's a cat or an act or a tack. I'm using the same 3 letters, CAT, but it depends how I sequence them. It gives me either an act, a cat, or a tack, which mean 3 different things, right? The same 3 letters rearranged in different sequence. So that's the DNA, that's how the DNA, the code, that's the information, how it's held right there, all right? So all those regions will code to particular proteins, which is just super, we call it elegant, because it's fascinating how the genetic code at the molecular level, it's universal. Every single animal and plant and bacterium and fungus that we found on Earth so far, with 2 million species, they all have DNA as a genetic code, all right? Except a few that have RNA. I'll talk about that in a minute. Basically, it's the DNA. So here is a map, a homologous map of bird, lemur. What's a lemur? A lemur is a type of, it's kind of like a monkey. It's a mammal, 4-legged mammal with a long tail. They're pretty. Guatimundi is, if you've ever been to Latin America, Guatimundi, we went to Guatemala, and this is the lemur. We saw them walking around. And they call Guatimundi, and they raise their tail high like that. They move in pods. So that's a lemur, okay? This type of monkey, I guess. So the chimpanzee, which is a primate, and the human, which is another primate, and the dog, the cat, carnivores, the cow and the pig, which are not carnivores, ruminants. You see the mapping that can be done by the sequence, by the percentage homology. In other words, which are most related here. By this percentage homology, the chimp and the human are most related. Let's follow this sequence. A, G, A, G, G, C, G. Here's discrepancy, C, G. C, T, G, G, T, T, G, C. Yeah. Another discrepancy, A, G. That's the second one, right? G, C, G, 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 C, A, T, G. T, G, C, G, A. Another discrepancy here. I'm just following the human and the chimp. T, 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 C, T, A, C, A, A. In 50 bases, 3 discrepancies. All right, in 50 bases. So that's the percentage homology. Very tight homology. Less tight, let's say, between the human and the dog, since they're next to each other in the sequence. Look at the non-homology, right? All of this is non-homologous between the human and the dog. You follow? This one, TT, is homologous. Then over here, nothing, nothing, nothing. A is homologous, this is homologous. This region seems to be the most homologous region. I think it's grayed out a little bit, I'm not sure. See, so this is how the percentage homology is actually done mathematically. It can be done mathematically by the sequence. That's why the human genome, that's why the genomes are important, because the genome is a sequencing of the DNA of the different species. And then we can do this, but of course it's statistical, because the human genome, we're how many millions on Earth? 7 billion, right? 7 and something billion. So 7,000 million. And did they sequence every single human being for the human genome? No, they sequenced about 100 humans. So those 100 humans is a very tiny fraction of the 7 billion that we are. But that's the human genome that is out there in NCBI and everything that is used in the computer for sequencing and for homologies and everything else. That's the standard. But it was about 100 people on Earth. No, they chose from different parts of the world and so forth, but several of them were the labs, Craig Venter and those guys that were doing the sequencing in the year 2000 and 1990s, the Human Genome Project. It's only 100 people, more or less, that did their DNA, okay? And that's supposed to represent, what if that is skewed? Which can be. But statistically, they figured that 100 was actually, as small as that number is, 100 was representative of the human population to be, 99.9999% accurate, whatever that is. So that's how we can do this mapping, all right, by the percentage homology. So we can just see by sequencing, by matching, of course, we don't do this by hand, right? The computers do this for us, and they give us percent, they crunch it, and they look at similarities, and then they give us the numbers at the end by percentage, and we just line out the percentage. The cow and the pig are more closely related than the cow and the cat. And the cat and the dog are more closely related than the dog and the chimp. And the chimp and the human are more closely related than the chimp and the bird, and so forth. So you notice all these are mammals, and the bird is out here because the bird is not a mammal, but is related somehow. So again, these would be now nodes. There would be common ancestors at each one of those nodes. And so if that is true, and organically we are mammals and we are primates, right? What does this say? That we are not chimps and the chimps are not us, because we cannot have contemporary ancestors. By definition, our ancestors are not contemporary, but we have a common ancestor. We have a common node, which is extinct, maybe in the fossil record if we find it. But the fossil record, by the way, I forgot to mention, is paucous, is the paucity of the fossil record, which is at the beginning. That word paucity means the scarcity, the lack. That's where we get poor from. Poor is lack of money, lack of fossils. So the thousands and thousands of fossils that we have now is very poor. Because contrast those thousands of fossils that we have discovered today, plants, animals, compare that to the millions and billions of individual organisms that have been living over the billions of years on Earth. So it's a very tiny fraction of organisms that we have. And even that also tells us something else. That fossil that we find, how do we know that that fossil is representative? Maybe it's an extra large specimen of that species that we find. So it's skewed. It may not be necessarily the norm, the representative, okay? And so that's what it means. The paucity, P-A-U, is the very few fossils that we have representing the huge number of organisms that have died over the millions of years pre-existing. Follow? Right? Okay, and even so, that paucity, those few remnants that we have, is just like the few stones that we find from an ancient civilization. Well, if we see 4 or 5 stones put together in kind of an orderly way, the logical thing is to assume that that was put there by some creature, all right? So it may point at some kind of ancient civilization. So the same again with the fossil record. So you see how the homologies are done, these maps, and it gets more sophisticated as we look at comparative between different species. They could be related or the percentage relatedness is what we look at with percentage homology. Basically, percentage relatedness, right? And that's being done at the DNA level, which is even prior to the protein. It's just depends what we're looking for. It's more expensive, more sophisticated at the DNA level, but it's also more accurate, right? And these are the homologies to the point that we can come up with an order called the Anthropoidea, the anthropoids, which has the old world monkeys, the new world monkeys, and the primates, and biologically speaking, Homo sapiens. Percentage homology, pointing to some kind of common ancestor. We haven't determined yet when or how. We should get there. Okay, the molecular clock, just like there is an atomic clock and an elemental clock for the radioactive decay, there is also a DNA decay, all right? And it's fairly constant. The rate of mutation in DNA is fairly constant for different genes, for different species. So this is kind of analogous to the radioactive clock, to the atomic clock of radioactive decay, similar. Organic molecules, DNA, mutates, all right? At a fairly constant rate. In other words, when the mutations are mapped out over millions of years, we get a straight line. We don't get a curve. That implies a linear relationship. A linear relationship is a fairly constant rate of mutation. And each gene in the DNA of each species will have a particular rate. It can be steep or it can be slow, but typically it's linear. It's a linear rate, which points at a constant rate of decay, with a constant rate of mutation. In that sense, it is different from the radioactive decay, which is not linear, it's geometric, right? Because it's halving at every time, halving the amount. And so the analogy is a loose analogy. On the one time, the atomic clock, because there's a radioactive decay and can be used for timing, for dating geological strata, but that is not linear, it is a geometric progression or regression. Whereas the mutation rate of genes is linear and also can be used for mapping or for trying to date ancestry when we look at percentage homology. Try to date ancestry by the rate of mutation. And also to point out that different genes, even though they typically have a linear rate of mutation, in other words, a constant rate, the rate could be middle of the ground, say average, like a 45-degree angle, or it could be steep, In other words, it could be a lot of rate of decay in relatively short period of time, or it could be very slow, right? A low angle. But that just tells us the amount of time, but the actual rate itself is linear, meaning that it's a constant rate, right? Okay, when we put all that together, we can come up with these trees of branching earlier and later. You can study this diagram a little bit more in detail, but over the millions of years, here is the rate of change, the mutation, the average change in the DNA by percentage. And therefore, the less change, the less rate of change, the closer the species, all right? So here we start at 5%, at 10%, within 10%, primates and mice. So they're closer together than, let's say, primates and birds are further away at 20%, all right? So therefore, birds and primates are diverge earlier than primates and mice, and so forth. And you do a regression going backwards, and you see the greater percentage divergence, the older the divergence, the earlier the divergence happens. Okay, and generally there's a trend to more primitive organisms as we go back in time, more primitive organisms, and their descendants today, because we don't have those primitive organisms, they are ancestors. But we have the descendants of the ancestors, for example, yeast, which is a type of fungus, all right? And so forth. These are descendants, but they imply an ancestor. Again, when we get to the node, those are the common ancestors. Finally, the big picture on the map, which is this is known today as the tree of life, or the largest cladogram, if you want, that has the 3 domains. Going to the 3 domains, and this is fairly sophisticated down to the level of, I think it's a phyla. These are phyla, about 30 or 40, and these 3 domains, as you can see, fall into eukaryotes, or bacteria, or archaea. Okay. For example, here is a super phylum of plants, but then they're subdivided. Can anyone find animals in here? Well, is it going to be in the archaea? Not in the archaea, because archaea are even more primitive than bacteria, right? It's not going to be in bacteria either. It's going to be in the eukaryotes. But where in the eukaryotes? Right here. Opisthocoms. Yes, the opisthocoms. Opisthocoms. Yes, it takes. I can't get it anymore. But this is the new classification, the sophisticated classification based on molecular homology. Based on molecular homology. Okay. The 3 domains, as you can see, is pretty sophisticated and is the most accurate so far. It implies a common root, which would have been the nearest common ancestor of all living species, and ancestral species, including the millions that have become extinct. We're going to stick to a more rudimentary classification, which still has the 3 domains, but has 5 or 6 kingdoms, depending on how you classify them here. For the eukarya, what does eukarya mean? Karyos is a reference to the nucleus, karyo, nucleus, in Greek, and eu, true or real. So these organisms have true nuclei in their cells. These are nucleated organisms. Organisms within their cells that have a true nucleus, which means that these other creatures up here don't have a true nucleus. So instead of being eukaryotes, they are prokaryotes. Prokaryotes means that they have a region of concentrated DNA or RNA, but they don't have a real nuclear membrane, which, by the way, is a double membrane, just like the cell membrane itself is a double membrane. It's a pretty sophisticated structure. The nuclear membrane to enclose the DNA and to protect the DNA. So it's a level of sophistication of protection of the DNA big jump between the prokaryotes and the eukaryotes, okay? So sticking with the eukaryotes for now, the most familiar ones are animals, of course, and then plants. So we got producers in the plants, consumers in the animals, but then there's this fungi that I kept mentioning. The fungi are closer to the animals than they are to plants, because even though they look like plants, that's why morphological, we cannot, can only go so far. You know, we have to go molecular. The fungi are actually closer to the animals molecularly. Why? Because they are consumers, they're not producers. They are saprophytes. In other words, they feed on dead organic material, but they don't photosynthesize. They don't photosynthesize. So the producers were first, in other words. Producers were first. They photosynthesize, meaning that they make their own food. And they got so good at it, they became food for other creatures, which are the animals. And then when the animals and the plants started dying, these other creatures came about, which are the fungi or the saprophytes, which feed on dead organic material. Okay? So those are the three large kingdoms that we're mostly familiar with, also because they can be seen. The unseen that are still in the eukaryotes are this grab bag called the protists. But this is like a pseudo kingdom, if you will, the protists, because it involves many, many different organisms that are not directly related to each other. The common relationship that they have pretty much is that they have true nucleus in their cells, and they tend to be microscopic. Okay, so we kind of lump them together. The amoebas and the euglenias and the protozoans and the paramecium and all that, and the different types of algae that we saw in high school biology. And then the other kingdom, the monerans, which are subdivided into bacteria and archaea. So now we're back in here into the prokaryotes with no organized nucleus, okay, the prokaryotes. Bacteria we're pretty familiar with. Many are beneficial, many are harmful, but they're ubiquitous, and thank God for them, because they are the microscopic saprophytes, right? They feed on organic material, dead or alive, and thank God for bacteria, otherwise we'd be covered thousands of feet of dead, rotting, decay organic material of all the plants and animals and fungi that have died over the millennia. Okay, so bacteria are constantly digesting all that. Anyway, there are also the cyanobacteria, which again, when I studied high school biology, they used to be classified as algae back then, the cyanophytes. But they're actually bacteria that photosynthesize. Very interesting because they produce basically the bulk of the oxygen that we are breathing today, about 3.5 billion years ago. We'll get to that next semester in more detail. But what's interesting is, all I'm trying to do is try to get to this group of archaea, which are bacteria-like, but they're not bacteria. They're more primitive than the bacteria. They're different than the bacteria, even though they're microscopic. They don't have an organized nucleus, but they're very, very primitive. They tend to be what is known as extremophiles. They live in extreme conditions. They live in boiling water, for example, in geysers. They live in UV exposure. And these are the archaea, are extremophiles. They live in very salty conditions, in brine, salt brine. They thrive in extreme conditions, you know. And some of them are called polyextremophiles, where they can live in extreme salt, boiling water, ultraviolet radiation exposure, anaerobic conditions, no oxygen. You know what? Those conditions are approximating the conditions in other planets. So these polyextremophiles can be put into a capsule, sent to those planets, and see what happens, because they could possibly survive there.
I think they have done, and one survived, one archaea. But not in planets, in space. They survived
in space. Yes, and possibly the moon. We don't know about it, but it may be going on the other side of the moon that we don't know about. This has also defense implications. It has all kinds of big implications. you know, that it's far-fetched, but it's doable. It's doable. It's doable. Exciting stuff. Okay. I have beaten you to death about the evidence for evolution, basically from the fossil record, the morphological similarities, embryological comparative embryology, vestigial structures, the biogeography, and finally the more sophisticated one at the molecular level with proteins and DNA. Okay. The only thing is I bracketed RNA because it is thought that before we went into a DNA world, it was an RNA world. It was a precursor. So precursor is considered to be, RNA is considered to be a precursor to the DNA molecule. It can still hold the genetic information, but it's not as stable and so forth. And the very last point, I don't know, I don't even have it in the slide. Oh, but it's in the sheet. It's in the handout. Let me erase that for a moment. This is my very last one. The DNA itself, okay, is a universal molecule of inheritance. A simple little analogy. Let's say we're gonna have a meeting or throw a party and we have a dozen people coming, and so we're gonna serve Kool-Aid, and we make the Kool-Aid in one large bowl, and then we put some orange coloring to the Kool-Aid, and then we fraction out, you know, a dozen glasses for our guests, right? Is any one glass not going to have the orange coloring? No. Every glass, every poured glass is going to have the orange coloring because we put the orange coloring in the bowl before we fractioned out the glasses. And so, by inference, every organism that is living today has the DNA as the molecule of inheritance. And the few that don't, which are typically bacteria, some bacteria have RNA, which could be considered a precursor of DNA. Functionally, it's the same thing. In other words, it holds the information. In fact, it holds the information faithfully from the nucleus to the cytoplasm to translate that information into a protein, okay? And so the burden of proof that evolution doesn't exist is on the ones who deny it. Because there's so much overwhelming evidence. And to me, the real clincher is the DNA. How can we have a universal molecule like that in every species that has been discovered as a molecule of inheritance? Again, the elegance on passing that inheritance just by a single cell from each one of the sexes, and even in asexual reproduction by a single cell to the whole next generation, you know, with tremendous fidelity. Okay, I rest my case. From now on, we're going to move as accepting the fact of evolution, and then I'm going to start giving you the mechanisms of how evolution may occur, all right? Which will get us into the next lectures. Questions, comments? We're good? Yes? Okay, so I'm going to shut down the recording. I need to, yes.
The slides that you are presenting,
Right.
Do they come up in the
Yes,
the YouTube presentation?
Yes, well, this is the YouTube is what I've been talking, all right? But what you're going to see in the YouTube is the slide presentation, including when I went online and all that, because the YouTube is essentially the desktop, what you're seeing,
Okay.
right?
Okay.
So in other words, this session is being recorded, which, by the way, reminds me, I need to get from you a consent form. I presume that you accept to being recorded if you ask a question or something like that. But I need to get that consent for legal purposes. I've neglected to do that, but I'll have the form available for you next time. Okay. All right. And also, I send you the actual PowerPoint as a PDF, which is lighter in megabytes. And I also send you this electronic. All right. Okay, well, thanks again. I'm going to shut it down now and start the download. So